Good morning and welcome to still basically week 8. We're finishing chapters 38 and 39. There is some unfinished business actually from chapter 38, namely the pair creations. It has to do with the fact that for high energetic gamma rays, because we moved actually a lot. We moved from the visible spectrum to the UV radiation when we explored the photoelectric effect. And then when we went to the Compton effect, we actually pushed the frequencies even higher. We pushed them to even higher frequencies when we reached the X-ray range. And that's where we saw the Compton effect. The Compton effect will not be visible, will not be observable for long wavelength, basically for the visible light or even for the UV radiation. So we really need high energies, okay? And when we reach extremely even higher energies, namely when we are in the gamma range, which is even higher than the X-rays, there is a potential for some other things that happen, and namely the pair creations. Basically, we'll have extreme high energies to the point that electron positrons will start to form, and that's exactly what was missing from chapter 38 to explore. Then we need to finish chapter 39. Chapter 40, as I was saying, basically it's going to come up with a brand new, basically, perspective on things. So let me share with you the screen. So this idea is actually still from chapter 38. So let me tell you exactly where we came in terms of frequencies. Obviously, we're not dealing with the longer wavelength. I mean, the infrared and the microwave and all of that. They're way behind us. Okay. So here is your red. Then here is your violet. This is the visible spectrum. This is what we can see. Then we entered the UV range. For the UV range, actually a little bit from here, we saw the photoelectric effect. These are extremely higher energies compared to the visible light. And of course, they are shorter wavelength, okay? Because don't forget that the dispersion law still applies. Lambda times frequency is still the speed of light. So the higher the frequencies, the higher the energies, basically, the shorter the wavelengths we're dealing with. We came to a range now from a nanometer to picometer, where this is actually the X-ray range, where we saw the Compton effect. And the Compton effect basically is the scattering of this high energy waves, very short wavelength. As a matter of fact, they have to be of the order of 10 to the negative 12 meters for this to be appreciable, because the shift in frequency, as the experiment and the theory has predicted, is of this order, this number times 1 minus cosine theta. In order to see a difference, this number was 2.427, 10 to the negative 12 meters, of the order of a picometer. So this lambda, the initial lambda, better be of that range in order to see a shift in lambda prime. Of course, lambda prime is longer, meaning that you're shifting backward in terms of energies, okay, to getting into this range. Once you hit even higher frequencies, okay, there is a potential not only that you would see probably the Compton effect, but also high enough energies for pairs to form. Namely, you create particles. Let me explain this last point. Imagine I have an extremely high gamma ray. Okay. Obviously, we have enough energy for it so that a pair of an electron and a positron form. What a positron is an electron except with a positive charge, that's all, okay? So it's exactly the same thing as an electron in terms of mass, in terms of other properties, except the charge in here, instead of being basically negative 1.602 10 to the negative 19 coulomb, which is a typical electron, this will have 1.602 10 to the negative 19 coulombs. Okay, so this is a positron, and that is an electron. Why do I need two of them? Because initially it has no charge. So Q is equal to 0. At the end of this is actually an explosion, the Q must be equal to 0. So the total charge must be conserved. This is one of the fundamental laws of nature, that the charge is a conserved quantity. So that's basically the reasoning behind it, and actually that's experimentally verified too, that you can have this situation. So here is the problem then. How much energy are we talking about? How much frequency, if you wish? What is the frequency, the minimum frequency for this process to happen? Okay, so all we have to do is do the energy conservation in here, and we'll see exactly what that is. In order to create this pair of charges, this pair of electron positron, to create them in such a way that they have no kinetic or no kinetic energy, they just were created. Basically, they don't. The minimum energy to create just them, not to give them, if you wish, extra energy, not to give them kinetic energy. So the minimum energy we're talking about in this case is twice mc squared. Remember, the expression for the energy when they are created, each and every one of them will carry with it this much energy. But I'm saying in here, make P equal to 0. Just this is the bare minimum so that you create them, okay? With no momentum. For that, each and every one of them will carry an energy of mc, will require an energy of rest energy in this case of mc squared, because the masses are the same. Both electron and positron have the same mass, and their mass is 9.1 10 to the negative 31 kilogram. So this is how much mass each of these two particles would require. Okay, so if that's the case, then what I'm saying in here is that this must be at least equal the minimum energy that I need to create this two particles. F is the frequency that is needed in this case. Okay. So how much is that? Well, there is a quantity that is worth memorizing for most of your calculations, and namely the rest energy of the electron. Okay, how much that is. All we have to do is multiply it by 2 because we have two of them, electron and positron. So the mass of the electron again is 9.1 times 10 to the negative 31, not 13, times c squared, which is 9 times 10 to the power 16. And I'm going to divide it. Instead of writing it in joules, I'm going to write it immediately in electron volts. Okay. So it's going to be 10 to the negative 19 electron volts. Furthermore, I'm going to write it actually in mega electron. I'm sorry. So joule will become in the denominator. I'm going to write it directly into a mega electron volt. Okay. So I'm going to divide by a million again. Okay. Because I'm having it in millions in here. So I multiplied by 10 to the power 6. I have to divide by 10 to the power 6. I'm multiplying by an electron, which is 1.6 10 to the negative 19, to convert it into electron volts. Okay. Anyway, so the 10 to the negative 6 and 10 to the negative 19 is 10 to the negative 13, and 10 to the negative 13 and 10 to the negative 31 is 10 to the negative 12. Or is it? No, sorry. I have to do 31 minus 3. What is this number again? Negative 31 plus 13?
I think it's just negative 31.
Negative 31, not 13. I'm sorry. Negative 31 plus 13 in the denominator, okay? So, or plus 29. Let's make it 29, okay? Because of the 16 in here. So it's going to be negative 2 after all the powers are gone. Please verify these things, okay? Part of me is right now worried about that thing. But anyway, so the point at the end in here is going to be 9.1 times 9 divided by 1.602 times 10 to the negative 2 mega electron volt, okay? And this number is 0.511, okay? Can you verify that thing there quickly here? 9 times 9 is 81 divided by 16 should be roughly about half, and that should be about 0.511 mega electron volts. Yes, no, maybe?
That's what I got.
Anybody? Okay, the internet is acting up again, okay? So this is number that is worth remembering anyway. So the frequency that I'm talking about in here is, again, HF obviously is equal to twice this number, which will put it at 1.022 mega electron volts. This is how much energy is required to make this happen. This is the minimum energy that is required for the photon to make this happen. Makes sense?
Yes.
Okay, all I have to do now, if I'm interested in the frequency, or the frequency is divided by h in here, which is 6.6 times 6.626 times 10 to the negative 34. I'm actually interested in the wavelength because all of this expression in here is really deals with the wavelength. So the wavelength, again, frequency is just from the dispersion law, c over lambda. So this becomes h times c over lambda, and that is equal to 1.002. Since we're going to convert back to back into the wavelength in meters, so it's probably a good idea to convert back to the joules. So this is from the mag back to joules. So lambda is going to be h, which is 6.26 times 10 to the negative 34 times 3 times 10 to the power 8 divided by this number, which is 1.022 times 1.602 times 10 to the negative 13. And the whole thing is going to be meters, of course, okay? I'm just going to focus on the order of magnitude for right now. 34 and 13 is negative 21. Negative 21 plus 8, that is negative, what, 13? And that is the order of magnitude. But don't forget, you have a 3, you have a 6, which brings it to about 20. 20 divided by 1.6 and 1. So it's going to be around 10, okay? Times 10 to the negative 13. So that puts it back into a picometer, okay? And that is the order of the wavelength that we're talking about. So this is the minimum wavelength, or the maximum wavelength, I should say, because remember, the wavelength is opposite, okay, to the frequency, which is the minimum energy. Having said the minimum energy or the minimum frequency, which is this much, means that this is the maximum wavelength you're going to need in order for you to create pairs. After that, any longer wavelength will not be able to create pairs. That's too weak of an energy. That's not enough energy to create pairs in this case. Okay? So this is basically the rationale behind the pair creations, and it has to do with a bare minimum. Of course, if we detect that these particles are moving and they have a velocity, then in this case, this energy from the photon is required to be even higher. So this is the bare minimum. So more energy than that, meaning shorter wavelengths than this, meaning we're really in the gamma range, then we'll create for sure a pair of electron positron, and that pair of electron positron is going to be moving with the velocity that is going to be given by this expression, the momentum basically that's going to be given by this expression, and the energy then, in this case, the wavelength is going to be then shorter than this one. I'm going to leave it to you guys to find the exact wavelength in here, but it should be of the order of 10 to the negative 12 meters. Make sense?
Professor, what's the exact value for H?
I'm sorry?
What's the value
H
for
is
H?
6.626 10 to the negative 34 joule second. That's a constant. That's Planck's constant. Yes?
Yes.
Okay. I know I introduced H bar earlier. One of you asked a question about it, but H bar and H are related in a simple relationship where H bar is H over 2 pi. That's the relationship between the two of them. So if you wish, H bar is roughly, I don't know exactly, so just divide 6.626 divided 6.28 is 110 to the negative 34. It's actually, there is some change in here, okay? It's 1 point something something, joule second. But I memorized H since a long time ago, so I use it, okay? So you can always plug in the value of H bar in here if you need it. And sometimes you will need H bar, not H. Make sense?
Yeah.
Okay, good. So this is basically the minimum value that you're going to have. The maximum value of the wavelength, I cannot really emphasize that enough because of the fact that the wavelength, if it's any longer than this one, that means you have really less energy. Because remember, the dispersion law relates the frequency to the wavelength, okay? So that means that any higher energies will plenty create your pair and probably give them momentum. But that means shorter wavelength than this wavelength that we computed. Okay, so this is the maximum wavelength. And any actually longer wavelength will mean that it's actually less energy because of this expression. Okay, this is the dispersion law that you discovered in chapter 32. Okay. One question that really is going to happen immediately, and we're going to talk about this one down the road, is once this pair is created, the electron can go about its own business because it's an electron, but the positron really is stuck in this universe where most of the electrons are actually, not most, all of the electrons are actually negatively charged. So it's going to encounter another electron if it's not the same one that it was created with, and basically annihilate again, okay, and re-emit that gamma ray, re-emit that energy that created it to begin with, okay? If it was just barely created, but if it was created with a high energy, high frequency, high speed, basically high momentum, so it's going to travel a little bit and then emit that minimum, basically energy, that minimum gamma ray that created it, and basically get annihilated in the process. Okay, that's basically how this process works. And this statement in here, you guys talked about the charge conservation in physics too?
I think so.
Okay, yeah, it's crucial for everyday experience. So this is true almost everywhere. Let me put it this way. I mean, in our daily experience, it's true no matter what. Okay, but somewhere near the black hole, near the event horizon of a black hole, this expression starts to break down. Okay, and probably we'll talk about that one. We'll talk a little bit about cosmology down the road when we explore the evolution of the universe from the vantage point of the four forces and the standard model. So it's almost true everywhere. Okay, let's put it 99.9% true in the universe. I mean, as a matter of fact, it's 100% true in our daily experience in the solar system, at least as we know it. Okay, so let's put it that way. But near the event horizon, there is a potential that when this pair is created near the event horizon, one of them will go basically inside the black hole, and the other one will come out of the black hole and be part of our universe. And then basically this charge is not conserved because one of them is gone and the other one is still here. And that's basically what happened. Okay, doesn't matter which, and both of them basically will change the charges of the universe. But that's near the event horizon, and that's something else. Okay, has to do with the information basically near the event horizon and the calculation of the entropy there. Anyway, forget about that point. In our daily experience, this is true. Okay, and that's why what we used in here for this pair creation. So this is part of chapter 38 actually, because I was looking at the notes in there and I saw that we missed on this point because you will need it probably for your calculations, also for the homework and all the things. Chapter 39, last time we basically had some unfinished business also with it, a lot actually. What we came up with is the experiment that confirmed the wave nature of electrons. So chapter 39 is actually, the problem is backward, okay? So it's, excuse me 1 second, I need to grab a piece of paper for use this one. So chapter 39 is actually backward in a sense that particles behave as waves. Chapter 38 is waves behave as particles. Okay, so and this experiment that basically later on was confirmed, since you can compute the wavelength in two ways. The first one is actually measuring it from the dispersion basically of the electrons on the after the accident that they ran into, and then also through using the expression that Mr. De Broglie has proposed for the electron. Since they can find exactly what's the momentum of the electron, then they can plug it into the expression and find the wavelength lambda equal to h over mv over the momentum, and that's it. And now they have the wavelength. Compare the two, and there is a match. So yes, electrons do behave as waves, and indeed they present the wave patterns. And actually, you can do the double slit on them. You can do the single slit, and they behave perfectly well as electrons. I mean, as waves. Namely, everything is for them is as a wave. So this is started to look like something basically slightly different in a sense that there is this pattern here that is emerging, that particles and waves are actually duality that is for all objects. Namely, for light, it's either a photon, which is a particle, or a wave, which is the normal wave. For an electron, it's either a wave or an electron, which is a particle. Okay, so this is basically where this thing started to emerge. In other words, in here you have a momentum p that is equal to h over lambda, and in this case lambda, and in here you have a lambda that is equal to h over p, where this has a more definite momentum, which is basically gamma mv. Okay, in general, gamma is the Lorentz factor, and in this case this is the photon momentum. Okay, plus their energies, their associated energies. Okay, so this is what the picture is now emerging for all of them. Before this experiment, Mr. Rutherford was exploring the idea how the atom is formed. We know the electrons exist. Actually, Millikan experiment measured their charges and the ratio of the charge over the mass. Okay, so we know that definitely that the electrons exist. Furthermore, we know that the atoms are neutral. Whatever constitutes matter is neutral. So the idea is the following, that the atoms must be some sort of a structure where the electrons are everywhere in here, and the rest of the atom is a positively charged distribution to cancel these negatively charged particles, which have definite charge and definite mass, because the total charge is equal to 0. Otherwise, we will be electrified. Everybody will have electricity flying every which way. So we know matter is neutral. Yet there is part of it that we know exists at that point, namely negatively charged. So the idea was floated that maybe the negatively charged are some sort of a dough, if you wish, where the chocolate chips are your electrons and the rest of the dough is a positively charged structure. In such a way, the whole thing is neutral. It's like I think they have a name for it. It's like the whole thing is basically has a 0 charge, yet because we know that there is a negative charge, so there must be a positive charge. So Mr. Rutherford in New Zealand was exploring this idea. So what he did was he took different kinds of thin films, basically, of metals, namely gold and silver and all kinds of metals. And he took alpha particles, which we know that they are positively charged. So we know the alpha particles that come from radioactivity, they have a positive charge. As a matter of fact, twice the charge of the electron. You need 2 electrons to cancel them. So the alpha particles have a positive charge of 2 twice. So if I shine this alpha particles on and basically run them through a velocity selector, so I know exactly where their kinetic energy is and their momentum and all of the properties that you would want to. And we know also their mass too, okay? So we know their mass how much it is. Basically, particle, so that you guys know, is now we know it's an ionized helium. Okay, so we run them through. They're extremely heavy. We run them through this foil, and because we know that the material has positive charge, we expect to encounter
DJ,
the positive.
your audio kept cutting out. Can you like repeat the last like 2 sentences you just said?
Okay, Natasha, I heard you. Is it still cutting or?
It's good now.
Okay, sorry about that. Anyway, so I'm talking about Rutherford experiment, basically around 1910, around that time. So his idea, as I was saying, is trying to explore the structure of this metals, basically, namely gold and silver and other metals, and he put them in foils, and he ran the alpha particles in here. You know how fast these things are. He expected an interaction of this alpha particles, since they are positively charged, to be repelled by this positively charged distribution of charge of inside the atoms. What he noted, though, is that for the vast majority of these alpha particles, they come unimpeded. They sail through. Only a small fraction of them were diffracted. So the vast majority go through completely and interacting with this positively charged distribution. So he concluded that the atom, really, the positive place is actually in a central location called the nucleus from the nucleus. So the nucleus is extremely small, where the positive charges are. So this picture is wrong then. And the rest of the atom is empty space because of the fact that the vast majority of the alpha particles go unimpeded. So this is the experiment of Rutherford. Okay, and that's what it concluded. So there is another nagging issue at that time, which was really a problem, and that is the mass of the different atoms. I mean, if you look, for example, at the mass of the hydrogen atom and compare it to that of the helium, for example, the helium is 4 times as much. Okay, but because we know that the hydrogen has 1 electron and the helium has 2, then there must be something different in there. Okay, so there was a particle at that time that seems to exist in the nucleus, but there was no evidence for it, namely the neutron. Okay, so the neutron will have another hypothesis that comes in later on. So at this point, we know of 2 things. We know that we have electrons going around in circles, or whatever path that they choose to go to, and we have the nucleus inside, a very tiny, small part of it. As a matter of fact, the distance in here is in the thousands of times, tens of thousands of times bigger than the actual size of this nucleus. So it's a huge distance, okay? So this is big. For example, if you take the model of the Earth and the Sun, the Sun is about 1 million kilometers, only 700,000, but let's say it's 1 million, okay? 700,000 is about 10 to the power 6 kilometers. I'm just taking the order of magnitude in radius. The distance to the Earth, though, which is one of the planets, there are 2 in here, is 150 million kilometers. So what we're saying in here is this is about 150 only orders of magnitude bigger than this one. This picture that emerged now is not the same. It seems like if the Sun was a nucleus, you have to put it not at 150, but rather at 10,000. which will put it way outside of Pluto. So Pluto is just in here, okay? This is put it way back. It's inside what is known as the Oort cloud. So this picture in here, if you think the solar system is empty, this is even emptier than the solar system. So the atom picture now is really, really different than what we thought in terms of the model that we had in our heads, that this is where the positive region only happens, okay? And it's mainly empty space, mainly empty, even emptier than the solar system, okay? And so that's really how the picture that emerged from that experiment. So Mr. Niels Bohr and everybody else tried to understand this picture. So the idea that was proposed immediately, that the atom looked like this. You have a nucleus, which is like the solar system, that is positively charged, and you have the electrons. The simplest of them is the hydrogen atom. So this is the hydrogen atom. Okay. Obviously, because this is negatively charged and this is positively charged, you have the Coulomb force, and the Coulomb force now is given by 1/4πε0 times the product of the charges, and I'm really taking it in absolute value, which is E², divided by the separation, which we know it's a huge compared to the size of the this geometry in here, divided by the distance squared. So this is Coulomb's law force, okay, between them. And if I were to apply classical mechanics, F equals to ma, this is mass times acceleration. Since I'm assuming that this is some sort of an orbit that is similar to that of how the planets move, this is just v²/r. The problem with this expression immediately is that this electron is accelerating, and its acceleration is given by v²/r. Okay? And because of the acceleration of the electron, if you guys remember your Larmor radiation from physics 2, that gives you basically the power with which it's going to dissipate energy, which is 2/3 times what? E² times the acceleration squared divided by 4πε0. That's needed for everywhere we have this chart, and times c³. Okay, is this correct? Is this what you did in physics 2 or not? Actually, it comes in as a problem. I don't think that you have the proof for it because the proof is a little bit complicated. But let me, does this make sense to you guys? I don't remember the exact formula.
Yeah, it does.
Okay, I don't remember it. But the point being in here, forget everything else. It's just this square term, the acceleration squared. That's the main thing, okay? And this, an acceleration, definitely, and it's a charged particle, so it has the charge. So I'm assuming in this expression from physics 2 is because usually you have q² in here, but I'm using the charge of the electron because I'm assuming it's the electron actually in the antennas, and the dipole antenna, it's the electron that goes back and forth and accelerated, and that's how the emission is given by this expression in here. Okay, so and it's the same thing. That's why I use E². I didn't use q² because q is equal to E now. The point being in here is that this electron in this model would radiate energy. This is the power, by the way, and power is energy per unit time. That means that this electron will lose energy continuously and will spiral into the nucleus. This is an unstable atom. And if you compute how fast it's going to spiral, it's going to take a fraction of a second. So the atoms should not exist if it were up to F equals to ma. If F equals to ma, atoms would have collapsed immediately after they form. Period. So when the atoms formed, it was about 380,000 years after the Big Bang. So at that time, there would be no atoms. Yet there are atoms. I mean, we're here to talk about them. We're made out of them. So this is not possible because of this radiation, because of the power being dissipated. This is the charged particle being accelerated, and this is the acceleration. If this model was correct, then the atom should not, if F equals to ma is correct, and this is what we use to find A from this expression, where the m is the mass of the electron, E is the charge of the electron, R is that distance I was talking about earlier. That means that the atom will, I mean, this is part of a problem, I think, in the homework also, where you compute how long it's going to last. It's going to last a fraction of a second, not even 1%, okay, of a second. So it's going to immediately collapse on itself and go spiraling, and the electron will fall onto the positively charged nucleus, and there will be no atoms. Any electron, it doesn't matter, will collapse, and there could never be atoms if this model is correct. So basically, the conclusion in here is also F equals to ma is incorrect in this perspective. We cannot really use it. However, Mr. Niels Bohr came up with a workaround for the hydrogen atom. Okay, and here is his idea, okay? First of all, it's really a long process through which he came up to the conclusion. At that time, we know again about HF, energy of the photons. So he knew about that. And he knew also about another study that was going on starting from 1885. And that is spectroscopy. Okay. Mr. Balmer, basically what he did was he looked at the different spectra of hydrogen, and he noted the following, that the pattern that is for light that is emitted by hydrogen, it has a frequency of the order of 650 nanometers. It has another frequency of the order of 400 something nanometers. I don't remember exactly. And then there is another one, 410 nanometers. And there is barely one that is probably visible, and actually is around 400, around 390 nanometers. Okay. So those are the frequencies. He noted this is Mr. Balmer basically observations. He noted that the inverse of these frequencies is given by a constant, later on called the Rydberg constant, times 1 over 2 squared minus 1 over n squared, where n in this case is greater than 2, okay? N is greater than 2, and you plug it into this expression, and it's going to work. This is an experimental result. Mr. Lyman later on, around 20 years later, around 1908 or something like that, he came up with a similar expression in the shorter wavelength. So Lyman came up with an expression in here that seems to follow this pattern. But instead of 2 in here, he has 1. And then Mr. Paschen came up actually with another study later on where it puts him in here. Furthermore, where n actually now is going to be, this number is actually 1 over 3 squared, which is 9, okay? Then, what is his name? Brackett, and I start to forget the names after that, okay? Came up with another range in here. Actually, there is an overlap in here between the two. And then there was another one, Fund, I think. And after that came in the 1950s, when after this one was well understood, came in Humphrey and all kinds of things. So there is actually a spectral analysis. So this is the emission spectrum. The absorption spectrum is the inverse, that's all. What the entire spectrum is showing, with the exception of this line is missing. So the spectral lines of the hydrogen were well known at that point. So Mr. Niels Bohr tried to fit this model, and he said that, first of all, the atom is stable, number one. And number two, for this emissions to happen, or this absorptions to happen, you have to have that the electron would transit from an energy level to another energy level. So he made these assumptions, and he followed his argument, and it led him to the following reasoning. I'm going to give you the simpler version of it. If you guys remember from your standing waves from physics 1, waves on a string, you could have, so this is a string, you could have half wavelength. So this is L, the length of the string, and this is the NT node, and this is a node, and this is another node. So this is one mode of vibration for the string. Or you could have the same thing in here, 3 nodes, basically, where the string could oscillate in such a fashion that it has 2 NT nodes, but 3 nodes. So this is NT node number 1. This is another NT node, and there's a node in here, and a node in here, and a node in here. This is another mode of vibration of the string. You guys remember this this picture from your physics 1?
Yes.
Yeah, and then it follows later on. You could have actually 3 NT nodes and 4 nodes, and so on and so forth. So those are the different modes of vibrations for a string where you have standing waves. His argument in a similar fashion, he said that the electron, while it's going around the nucleus, so this is your nucleus, and this electron will form also standing waves. And as this wave closes in other words, you have multiple wavelengths of this path, the path of this distance is r. So the path is 2 pi r, that's all. So that's the circle, okay? Must be multiples of the wavelength, multiples of lambda. If it is multiples of lambda in some sort of standing waves, then the electron is stable in its path, and there is no dissipation in this case because of the breakdown of classical mechanics. And you don't have this problem. What is it? The one what I was talking about in here, this thing in here. So the electron is stable if you have this condition that you have standing waves in this pattern, similar to what you have seen in physics 1, with the exception now that the path, instead of the length of the string, the path itself is multiples of the wavelength. Okay, sounds good? So this is his assumption.
Sounds good.
Okay, so if we follow this rationale, so for n equals to 1, 2 pi r must be exactly a wavelength of the electron, and so on and so forth. Lambda is again given by de Broglie's expression. Lambda is just h over mv, the momentum. Okay, h over p. So that is the wavelength of the electron. So if we do that, that means that 2 pi times the radius, now it's going to be dependent on this index n, because this is an integer. So I'm going to call it Rn, if you guys don't mind, because it's not the same radius for all the electrons, because depending on n, now it could have n bigger or smaller, because n could be 1 or n could be 2 or so on and so forth. So in this case, it's going to be n times lambda, and lambda is just h over p. And probably p also depends on n, because now it depends on what I choose for n. If n is equal to 1, I probably will have 1 energy level. For n equals to 2, I will have another energy level, and that is exactly the number that is going to show itself in here. So this is going to be what is known as the principal quantum number. N is the principal quantum number. Okay. So in this expression, then I'm going to move the Pn to the other side and move the 2 pi to the other side. This is how it's going to be like. It's going to be R times Pn is equal to N times H over 2 pi. This is the first time that H bar is going to show itself. So this is NH bar, where H bar is just H over 2 pi. So instead of carrying this 2 pi every which way, so we called it H bar. So this is the constant H bar. So what you're asking in here is, what is H bar? It's just H over 2 pi, okay? H is a constant divided by 2 pi, which is a constant. So it's going to give me a new constant instead of writing it that way, where it's just H bar. So this quantity in here, the radius times the momentum in classical mechanics, this is R, this is the momentum, which is mv. That is nothing but the value of the angular momentum. So the angular momentum is actually a vector that is equal to r cross p. And if I take the magnitude of this vector, all I'm going to find in this case is r times p times the sine of the angle between them, which is 90 degrees. So it's going to be rp. So this is the angular momentum. So the angular momentum is quantized. What I mean by quantized, it comes in increments of h bar. It comes in increments of h bar. Obviously, n cannot be equal to 0, because if n is equal to 0, first of all, this expression blows up, okay? And second, that means that the electron is sitting right on the positron, and there's no atom in there. I'm sorry, sitting on the proton, is sitting on the nucleus, and there is no atom in there. So n cannot be equal to 0. So n is anything but 0. So n is 1, 2, 3, 4, 5, 6, 7, and so on and so forth. Okay, cannot
Professor?
be equal to 0. So, yes.
What does L represent?
L is the angular momentum. This is from physics 1, by the way. Okay. This stuff in here. Yes. Does this ring a bell?
Yes. And then N is that the
Very
distance
good.
between, that's not the radius, right?
N is just a number. N it is an integer. N is 1, 2, 3, and so on and so forth. It's the principal quantum number.
But what is a principal quantum number?
R is the radius. R is the radius. So from classical mechanics, for a point particle, the momentum is r cross p. And in this case, because the radius and the momentum, the velocity, are actually perpendicular, so that's why I'm getting, actually, it's not this angle, it's this angle. This is r and this is p. This is a 90-degree angle, and sine of 90-degree angle is 1. So that's why I wrote the angular momentum in magnitude just r dot p. R multiplied by p. Okay, remember that this is the angular momentum is a vector too. Okay, sounds good.
Yep.
Okay, so we're in good shape now. So this is the deal now, that the angular momentum is quantized and comes in chunks of h bar, or h over 2 pi if you don't like h bar. Okay, always either 1 of 2 h bars or 2 of h bars or something. It can never be 0 though, because if it's 0, then you don't have an atom. Okay, so this is the condition. Then, and this is the mistake, then use F equals to MA. Okay, but we're gonna do it anyway, and you will see how immaculate this is gonna work. Okay, it's like magic. So let's go back into F equals to MA. Remember, F is equal to, again, for this problem is 1 over 4 pi epsilon naught times the 2 charges. I'm taking it in magnitude. I know the direction is going to be pointing toward the nucleus, so I'm not going to care about the signs anymore, because divided by that radius squared, and that radius depends on the integer number n now, is equal to the mass of the electron times the velocity, again, that depends on that integer. Okay, remember, because of this expression, this 2 Rn and Pn, which is, and Pn is just MVN. So I can write it, actually, let me write that expression a little bit better. I'm gonna write it quickly here. So again, where Rn times MVN is equal to NH bar. Okay, that is the new addition to the whole problem. If we do that, then we can compute the energy right away. The energy in this process is equal to, this is the total energy, is equal to the kinetic energy, which is 1/2 of mvn squared, plus the potential energy. The potential energy in this case is going to be negative, because again, use of n is going to be 1 over 4 pi epsilon naught times the product of the 2 charges, and that is where the number is going to be negative, divided by the distance. So this is the potential energy in this case. So it's minus 1 over 4 pi epsilon naught times E squared over Rn. Okay. Well, I can find MVN from this expression. So this is going to give me what MVN is, or what the velocity is, because I need it in here to compute this value in here. So Vn is going to be equal to NH bar. This is NH bar over MRN. And sub it in here, and we're in business. So we're going to find the total energy, En, is going to be equal to 1/2 mass times this expression squared. So that's going to be m squared h bar squared divided by there is another term in here. Oh, this expression. I'm sorry. This expression actually right away can give me the answer. I'm sorry. This expression right away can give me the answer because I have, let me cancel Rn in here and Rn squared in here. I have in here mv squared in here. You guys see that? From F equals to ma. This is F equals to ma. This is F. This is mass times acceleration. So, and the acceleration for the circular motion is the velocity squared divided by Rn. That's why I used it this way. So in this case, I have mvn squared is exactly equal to 1/4πε0 e squared over Rn, except I have a factor of 1/2 in here. So basically what this expression for the total energy is going to look like now is the following. 1/2 times mv squared is going to be 1/2 times 1/4πε0 times e squared over Rn minus 1/4πε squared times e squared over Rn. Obviously, I didn't need these terms at all. Obviously, from this expression, I don't need this right now. I can find this difference in here between them and note the following. This is exactly the same term, except this is half of that. So the whole thing is going to be just negative 1/2 times the whole potential energy. So En right away is going to be equal to negative 1/8πε0 times e squared over Rn. Okay. Now, let's so we have two equations for Vn and Rn. We have this equation for Vn and Rn, and we have this equation for Vn and Rn too. Okay, so we're going to eliminate one of them in favor of the other, and we're done. This is from F equals to ma, and this is from the other one. So let me rearrange those expressions so that you guys see exactly. So that we have, first of all, 1/4πε0 times e squared over Rn is equal to mv squared n. And then we also have m Rn Vn equals to nh bar. Those are the two expressions that I need to solve simultaneously because I don't know what the radius is. I don't know what the velocity is. Once I do that, then I can come back to this expression for the energy in terms of Rn2. Okay, so we can find what the expression of Rn2. So it doesn't matter which one we eliminate. I'm going to eliminate Vn in terms of, like I started doing in here, Vn in terms of Rn. So Vn then is equal to nh bar divided by the mass Rn. Now we plug into this expression and we will find then an equation for Rn. So 1/4πε0 times e squared over Rn must be equal to the mass times this quantity squared. So the mass times n squared, h bar squared divided by the mass squared, Rm squared. Obviously, Rn squared and Rn cancel. M squared and M cancel. And we move the terms around and we found already the expression for Rn. And Rn then is going to be equal to, when I move it to the other side, it's going to be equal. Let's put M squared in here. And then I have h bar squared times 4πε0 divided by e squared m. So I have the mass because I am left with one m in the denominator, and I have e squared. So this is the radius of the electron expressed in terms of everything, including n, this integer that we introduced. I know what 4πε0 is. I know what h bar is. I know what the mass of the electron is, and I know what the charge of the electron is. So all I have to do is plug in these numbers. 1 over 4 pi epsilon naught is just equal to 9 times 10 to the power 9. Everything is in SI right now, okay? H bar is just H over 2 pi, which is 6.626 times 10 to the negative 34 divided by 2 pi. And then I have the mass of the electron, which is 9.1 times 10 to the negative 31 kilogram. And I have the charge of the electron, which is 1.6 times 10 to the negative 19 coulombs. I have everything in this expression. So if I plug it in, I will find that this number is equal to about half an angstrom, or 5 times 10 to the negative 11 meters. Okay. So this number in here is a constant. So Rn is equal to A naught, I'm sorry, A naught, not A naught squared, times N squared, where A naught is equal to 0.5 angstrom, or 5 times 10 to the negative 11 meters. I didn't plug in the numbers, so I'm going to leave it to you guys to plug in the numbers and verify what I'm talking about here. Don't forget, it's not 4 pi epsilon naught, that is 9 times 10 to the power 9. This is already, when you plug in the expression, has already 1 times 9, 10 to the power 9 already in it. It's actually 8.99 something, okay? Times 10 to the power 9. And then H bar is going to be 6.626 times 10 to the negative 34 squared divided by 4 pi squared. This is this term. Then the mass of the electron, which is 9.1 times 10 to the negative 31, and times E squared, which is 1.6 squared, 1.602 squared to be more specific, times 10 to the negative 19 squared, that's negative 38. So you're dealing with negative 64 in here in terms of the power. Don't forget the 6 squared in here. And you have a negative 31 in here, and you have a negative 38 in here, and you have a positive 9 in here. So at the end of the day, when all of this power settle, you will have a 10 to the negative 11 in here. And then the other numbers, they roughly come out to about 5. You guys understand what you can do in here?
Yep.
Okay, so it's easy. So this is called the Bohr's radius. So n equals to 1 is the lowest radius, and then n equals to 2, it's actually 4 times further away, and equals to 3 is 9 times, and so on and so forth, because of this expression. So we found the radii. Then all we have to do is plug in the expression for the velocity, and then we're in business. So the velocity Vn now is equal to n times h bar divided by the mass times this number. The mass times this whole thing. Rn, which is, I'm going to just write it as n squared A naught, okay? Where A naught is that's this number in here. The n and the n squared cancel, so the velocity now seems to drop like 1 over n. So mass times A naught, and then you have 1 over n. So again, n is appearing in it as we thought it should, okay? Because we introduced it at some point because of that constraint on the path of the electrons, that it has to be in some sort of standing waves. Then it appeared everywhere. It appeared in the velocity, it appeared in the, and it appears also in the energy. Let me go back now to the energy, because now we are ready to do the energy. The energy now is in good shape. Where is the energy in here? Here is our energy, because it depended also on Rn. And because Rn depends on n squared, this term also is going to depend on n squared. So let me rewrite the expression for the energy now. The energy is going to be equal to negative. And it's a negative value because it's a bound electron. Because if it's not negative, if it's 0, for example, there is no reason why the electron should stay next to the hydrogen atom. If it's positive, then the electron has plenty of energy to escape the hydrogen atom. So it has to be negative to basically be stuck with it. Just like when you guys did the solar system, you also found the total energy for the planets or the satellites as they orbit the Earth, or the moon as it orbits the Earth. That those things have to be in negative energy because it's bound to it, the total energy, okay? In other words, it doesn't have enough kinetic energy to escape the whole thing. Remember, the total energy is the kinetic energy term plus the potential energy. The potential energy what keeps it together. And this kinetic energy, if it's anywhere bigger than this potential energy magnitude, this thing will escape. But the total energy we found in the moon, okay, when it's not excited, it doesn't have enough energy to escape the hydrogen atom, and that's exactly what we want, okay? So the negative sign has a big meaning in here. So it's negative 1/8 pi epsilon naught times the charge squared divided by this number Rn. So I'm going to write it in its full-fledged, okay, because I want to put some terms in it. So we have n squared. That's this term. What is it? This term, the first one, times 4 pi epsilon naught h bar. 4 pi epsilon naught times h bar divided by the mass times e squared. We're going to write the mass in the numerator then. And instead of e squared, okay, let's leave it e squared. So it's going to be e to the power 4 now. So what we have in here, we have negative. I'm going to write the 1/n squared first times the rest of the stuff that we know what it is. So this is m e to the power 4 divided by 2 times 4 pi epsilon naught squared, because you have two of them, 4 pi and 4 pi in here, epsilon naught. And then you have the h bar, okay? So this is the entire expression for the energy. Again, you know what the mass is. The mass is 9.1, 10 to the negative 31. You have E. I'm going to write E cubed. I'm not going to write the expression with E, okay? So I'm going to write 1.602 times 10 to the negative 19 cubed. And I will tell you why. Because I want the expression to be in electron volts. So if it's an electron volt, I'm going to divide by one of them anyway. So instead of putting it to the power 4, I'm just going to write it to the power divided by 2 times h bar. H bar is 6.626 times 10 to the negative 34. But then I have to multiply by 2 pi in here because of the h bar. And then this 4 pi epsilon squared is going to be another thing in the numerator, which is 9 times 10 to the power 9 squared. If I plug in all of these numbers, first of all, I have a negative 31 in here, and I have a negative 57 in here because 19 times 19 plus 19 plus 19 3 times is 57. Negative 57 and negative 31, that put me negative 89 or something like that, or 88. But I have a negative 34 in here, but don't forget I have an 18 in here. So when all of these things are said and done, did I miss a term in here in h bars? Was it in h bar squared? Yes, in h bar squared. I'm sorry. So this is 4 pi squared. So this thing is squared. Okay, that's better. Okay, because of the fact that now I have the negative 64 in the denominator, and I have a negative 57 in the numerator, and I have a negative 31, and I have a positive 18. So that now is better because both of these numbers, 57 and 81, 80 something minus, so it brings it to around the order of magnitude in the ether should be negative 13.6 electron volts. Okay, verify this stuff. So this is not an h bar, it's an h bar squared. Because that's how the expression for Rn is. Sounds good, everybody? So this is the energy levels and
That's the value I got.
okay. So the energy En mainly is equal to negative 13.6 electron volt divided by n squared. If you don't like it in electron volt and you want it in joules, all you have to do is multiply that number again by the missing E that, remember, we cubed it in here. We have to multiply by 1.602 times 10 to the negative 19. And that's going to be in joules. Okay. So it's going to be a negative 18 something, 10 to the negative 18 something joules. Okay, so this is the expression that we have for the energy of the electron. Now we're ready then to interpret. So this is an important result. Then we can understand what's going on with the different spectra of the hydrogen. Before we do that, there is another way of rewriting this expression, and that involves the speed of light. Okay, so I'm going to introduce the constant R, and the constant R has to do with these numbers. What is all of these numbers basically without the n squared? Multiply them and divide them by hc, and you will see the reasoning behind the hc. Before let's not introduce R. We can do it quickly in here. Okay, so the energy En minus the energy En1 minus the energy En2 must be equal to the h times the frequency that is emitted, provided then in this case that the ending, so this is N1 and this is N2, the difference in energy between them is the frequency that is emitted or absorbed, depending on the sign in this case. Okay, so the delta E will determine exactly the difference in energy. If it's positive, that means it's emitted. If it's negative, so you have to plug in the negative value in here, and that's going to be absorbed. That's all, because the lines of absorption spectra are going to be the same. So in this case, all I have to do is going to actually, this is the N2, this is the final, and this is the initial. Okay, it doesn't matter. All I'm going to do is here put in the expression that we just found, which is negative. You can write this expression as negative E naught divided by n squared, where E naught is at 13.6. So it's going to be an E naught divided by n squared, 1 minus E naught minus E naught divided by n2 squared. Remember, the energy is negative for it to be bound. So it's going to be basically, in this case, E naught times, this is going to be positive, so it's going to be 1 over n2 squared minus 1 over n1 squared. Okay, obviously my representation here is a little bit not great because of the fact that n2 is less than n1. Typically when we have the indices, I mean, remember, they lower the energy level, the less the number. In other words, okay, n2 is equal to 2 for Balmer, then n1 can be any number greater than 2. That means 3, 4, 5, 6, and so on and so forth. Okay, if n2 is equal to 1, that means that we're dealing with the Lyman. I think there are 2 n's in his name, I'm not sure. Then in this case, n1 can be any number greater than 1, meaning that 2, 3, 4, and so on and so forth. Okay, but for the other one, for passion, for example, n2 is equal to 3, and that is passion. But in this case, n1 can be any number greater than 3, any integer greater than 3. That means it's 4, 5, 6, and so on and so forth. And you guys get the picture. For n2 equals to, I think, what is that, bracket or whatever the name of that? I think I start to forget the names after passion. So 4, then in this case, n1 can be any number greater than 4, which is 5, 6, and so on and so forth, if you can detect them, because some of these numbers, they become so close from one another. And as a matter of fact, if you draw the energies, I did not draw them, this is n equals to 1. N equals to 1, n equals to 1, that means the energy E is exactly equal to negative E naught over 1 squared, which is equal to negative 13.6 electron volts. For n equals to 2, remember, it's very far away. E2, so this is E1, E2 is equal to negative 13.6 divided by 4. So this number is negative 13.6 divided by 4, which put me at, we got a calculator right here. 13.6 divided by 4. So in this case, it's negative 3.4 electron volt. And for n equals to 3, actually it's going to be E3 is going to be negative 13.6 divided by 9. The number is getting very, very close from 1. So at the end is going to be (1.5 electron volt). So the gap in here in energy is negative 3.4 minus 13.6 is 10.2 electron volts. It's a big gap between the second energy level and the first energy level. Okay. Whereas in here, between 3.4 and negative 1.5, it's barely noticeable. So this is n equals to 3. And in n equals to 3, the energy level is negative 1.5 electron volts, and negative 1 over minus. Let me do the algebra quickly in here. So it's 1.9. See the gap in here? 1.9 electron volt. How about n equals to 4? The energy level for n equals to 4 is going to be negative 13.6 divided by 16. Negative, it's going to be less than 1 anyway. (0.85) with a negative sign still. So the gap is going to be even smaller. Negative 0.85 minus 1.5. So it's going to be what? (0.65 electron volt). So the gap, as you can clearly see, as n increases, starts to shrink until you get into n equals to 4, n equals to 5, n equals to 6. So even if you go to n infinity in this case, which brings it to 0, n equals to infinity, then that means that you are at that point in here where the entire gap is your 13.6 electron volt. You guys see the difference in here, what I'm talking about in terms of the energy levels and how they start to get closer and closer from one another as n increases?
Yes.
Okay, here is the transitions then we're talking about. Let me pick up a different color for the pen. I'm going to use a blue line for Lyman. Lyman, the terminating frequency is always n equals to 1. So all of these transitions, they're possible. So on and so forth. So all of them, they correspond to high frequencies. As a matter of fact, 10.2, which is the lowest frequency, which is the longest wavelength, would put it in a region that is in the UV region, because 10.2 electron volt times 1.6, if you care, times 10 to the negative 19 joules divided. This is the energy E. Remember, is equal to hc over lambda. From here, we can find how much wavelength we're talking about. We're going to find h, which is 6.626 times 10 to the negative 34, times the speed of light, which is 3 times 10 to the negative 10 to the power 8, divided by this energy, which is 10.2 times 1.6 times 10 to the negative 19. Okay, negative 19 and negative 34 is negative 15. Negative 15 and positive 8 is going to be negative 7. So this is 10 to the negative 7 already, but you have 3 times 6, 3 times 7, which is about 27 divided by 2, divided by 10. That should put it, this is the longest wavelength, which is the smallest energy for Lyman, okay? That will put it right at, what is it, did I say? About 27, 30 divided, so it's about 3. So I didn't do the math in here. Hopefully you guys will do it. 10 to the negative 7 meters, okay? 10 to the 7 meters. So it's actually less, because 6.6 times 3 is less than 30. So this number is about 2.7 or something like that, okay? 2.7 times 10 to the negative 7 meters. If I want to convert it to nanometers, how we measure frequencies, all I have to do is divide by 10 to the negative 9, and then that's how many nanometers are in a meter. So cancel this, and I will have 10 to the power 2 in here. So in other words, the shortest I mean, the longest wavelength, not the shortest, the longest wavelength is going to be 270 nanometers. And remember, the spectrum cuts off around 400 nanometers for the visible light. So this is well inside the UV radiation region. So this puts me, and this is the longest wavelength, because this one is definitely shorter. Add 10 to 0.9 to 1.9, so it's going to be 12.1. 12.1, so instead of dividing by 10, I'm going to divide by 12. So the next wavelength is going to be smaller than this one. So that will push it even further in the UV radiation. That's why the UV radiation was in that range, was not visible, was in the UV radiation for Lyman. But when the terminating value is exactly in n equals to 2, then in that case, we should be in the visible light. Let me pick up the green in here. The longest wavelength is going to be between n equals to 3 and n equals to 1. N equals to 2, I'm sorry. And that is 1.9. So instead of dividing by 10, I'm going to divide by 1.9. So let's see what that value is going to be. Lambda is going to be 6.626 times 10 to the negative 34. Again, that doesn't change. Times 3 times 10 to the power 8 divided by, now it's 1.9 instead of the other number, times 1.6, 10 to the negative 19. Again, 10 to the negative 19, all of that is going to reduce basically to 10 to the negative 7. We did that already. All I have to do is 3 times 6.6, which puts it around 27, divided by 1.9 times 1.6, which is around 2.5, okay? So the wavelength now is going to be, what is it, 3.5. 2 times 1.6 is about 3.5, okay? So at any rate, 27 divided by 3 is roughly about 10, okay? 10 times 10 to the negative 7. I'm just getting an order of magnitude in here. I'm not really doing all numbers in here. So again, 10 to the negative 9 to get it into nanometers, because this is actually was in meters. So I'm going to convert it in here. So that will put it 10 to the power 2. Again, so this will put it around 1,000 nanometers. It's actually, if you do the math, and I didn't do it in here, it's going to be 656 nanometers. And this is the red light. The red light in the Balmer series. When I did the order of magnitude, I'm getting this rough number of 10, which is about 6 actually. 6.56 times 10 to the power 2, which put me at 656, okay? And this is actually the longest wavelength. I can get shorter than that by, instead of doing 1.9, add to it 0.65, and we'll put it around 255. So instead of dividing by 1.9, I'll divide by 255. So definitely the next number is going to be less than this one. And that is going to be the blue light. And then I can go to the next level, which I didn't compute in here, and add to the other 3, and I'm going to find that spectrum. So Balmer will be really in the visible range between 700 and 400, at least for the most part, okay? And then, of course, if I'm interested in the other ones, for example, the Passion series, all I have to do is the longest wavelength I'm going to get in this case. I'm sorry. Not the longest, the shortest in this case is going to be dividing by this number, okay? So instead of dividing by 1.9, we're going to be dividing by 0.65, and that's going to put it definitely in the thousands of nanometers. So that's going to put it in the infrared. Does this make sense to you guys? I mean, at least from these formulas that you can get all of those spectra?
Yep.
Yep.
Okay, here is a nagging issue though, and this is, we're going to come back to it. The theory matched the experiment up to 0.1% in all of them. So this is a success beyond the doubt. There is no doubt about it, except that that nagging issue with the 0%, everything was beautiful, immaculate. So this theory looks like it's really on a great path. So in order to correct that 0.1%, the mistake we did was when we assumed that the nucleus is fixed and somehow the electron is going around it. And the central body theorem requires that these two actually revolve around the center of mass. So instead of taking the problem as being an electron revolving around the nucleus, we have to take actually the nucleus, which is the proton, also wobbling around. So for that, we're going to introduce the reduced mass and to find the center of mass. And the reduced mass in this case will be just the mass of the electron plus the mass of the proton for the case of the hydrogen atom, divided by the mass of the electron plus the mass of the proton. Sorry, multiplied divided by the mass of the proton. So this is the reduced mass. If you calculate the angular momentum, the moment of inertia in this case is going to be the sum of the two, that of the momentum of the proton times the radius of the proton squared plus the momentum of the electron times the radius of the electron, and you use the center of mass instead. So the problem will resolve to this equation at the end of the day, okay? So you treat this equation as the reduced mass times some radius, and that radius r is actually the distance between the proton and the electron, okay? I should call this one is reduced, RR, okay? So, and this is actually the interatomic distance that we've been using all along. So this one will be the electron distance, and this is the electron distance. And this is now the interatomic distance between the proton and the electron that we measured already, we calculated already. So if we do the calculation in here, squared, I'm sorry. Okay. If we do the calculation in here, and we know that the mass of the proton is roughly about 1800, 1900 times that of the electron. If we plug in the equation in here, we have 1900, the mass of the electron times the mass of the electron, it's the mass of the electron squared. 1900 plus 1 doesn't matter, so it's 1900 plus 1, it matters. That's where the percent is coming from, actually. The mass of the electron, cancel this mass, cancel that mass. This is roughly 0.997, 0.99 the mass of the proton, because 1900 divided by 1901, that is where the discrepancy is coming from. So that explains that 1% error. Other than that, the theory and the spectral lines match beautifully. So Mr. Niels Bohr was excited about this result and this theory. It seems to work beautifully. So how about helium? It fails miserably. You cannot use it for helium or lithium or any other element in the periodic table. It works only for hydrogen. That's it. Unless you take helium and you remove one of its electrons. So you have an ionized helium, then it works. Or lithium, and you ionize twice. Then in this case, you'll have only one electron to deal with. These are called hydrogen-like atoms. Other than that, it doesn't work, no matter what you try to do to it, okay? And so this is the state of affairs around that time, and we were left hanging, no matter how he tried. Mr. Niels Bohr's model is not going to work with the exception of the hydrogen atom, okay? We're going to take a break. Right now, it's 9:24, 25, okay? We're going to take a break. We need to get into the black body radiation, and we're done with this unit. And we'll probably, we're going to talk about the lab, and you will see how amazingly this lab is easy for this section, for the photoelectric effect. And we're going to probably have one or two problems, and we're going to discuss the rest of them. Sounds good?
Yep.
Sounds good.
So I'm going to put it on a, I'm going to stop the recording. We're going to take a break for about 15 minutes. So we should be back around 9:40, isn't it?
Yeah, that's right.
And we will, okay, so I'm going to, again, welcome to the second part, basically, where, as I promised, we will try to finish this whole topic, and then set up the stage for what comes next. and also talk about the lab. As I was saying earlier, this lab is really easy, with the exception that there is an issue that has changed from when I made the instructions for this lab, namely the FET website. And we're going to do at least a couple of problems from these two chapters and talk about the rest of them. So let me share the screen and tell you all along that we were doing this backward, for the fact that we were mentioning Mr. Planck, Mr. Planck, Mr. Planck all along, but we never talked about what he did actually, okay, and how this thing was started, okay. And so the expression that really started the whole thing is this expression for the energy of a photon that we're assuming somehow it has to do, is proportional to the frequency. But this constant h was introduced by Mr. Planck himself. Later on, this constant was named as Planck's constant. Okay. The spectra that we've been dealing with up to this point, they're really for individual atoms. And how can you find individual atoms, for example, hydrogen or whatever element you're talking about? Most of the times they're in low density gases. So if it's the case, then you can have, when you shine a radiation on it, when you shine light on it, it's going to absorb those spectral lines, and they're going to be missing from your spectral lines. So this is an absorption spectrum. Or you put them in a tube and you put them under a huge voltage, again low density, to make sure you're dealing with as much as possible individual atoms. Then in this case, and you excite them, you put them under tremendous voltage, for example, and at that point, the light that is going to come out, it's going to come out with this spectral lines. That is the emission spectrum. So in either case, that is basically what you are dealing with, a low density material. But when you have a higher density of that material in a liquid form or a solid form, then the spectrum becomes to be fuzzy, because you will have a lot of the atoms basically next to one another, and they are all emitting in different regions, especially with different materials. And at that point, the line becomes more continuous. In a sense, you will not find a single line by itself, but a spectrum that is continuous for the entire spectrum. All the wavelengths are going to be represented, basically. That is the continuous spectrum for an emission, for example. Or an absorption is going to be the same thing. You shine a whole bunch of light on a material of these properties, a solid material, for example, is going to absorb everything. You're going to find nothing on the other side. All the lines are basically missing. So that is a continuous spectrum. A continuous spectrum is usually dealt with when you're dealing with the bulk of material. It's easy to do actually in your home. All you have to do is take a piece of iron, like the spoon, for example. You have to be careful when you do this, because you have to have an insulator, and put it on a heat source. Okay, that is similar to your voltage. So it's going to excite all of the materials in there. That heat source absorb all of those energies and starts to emit that radiation. And that radiation is going to come in the entire spectrum, depending on how much temperature is going to reach, though. The higher the temperature, the more excited energy levels are going to be, and the entire spectrum is going to show. The material light starts to change color, actually visible. You can see it actually in the dark red, and it's going to be brighter red, and then yellow, and then white, where white really now is all of the wavelengths are going to be represented, provided you did not reach a phase temperature for that material, it starts to melt, okay? Because if it does, then other physics is involved. So an idealized version of that is the so-called black body radiation. So what the black body does is it absorbs everything that you send to it. And if you excite it, it's going to emit everything you wanted to in the spectrum. So it's a perfectly absorbing material and a perfectly emitting material. Obviously, this is an idealization. There is no such a thing as black body radiation. Just like when we were dealing with the ideal gas law, that is basically what we did. We gave up with some properties that are an extreme in every which way, and we came up with sample relationships. So this is an idealization of the similar problem for the continuous spectrum. Now we're dealing with everything, all the waves, all the wavelengths, I'm sorry, okay? that you can think of. So the problem was famous, and people study it and try to understand it toward the end of the 19th century. Okay. Here is when they measured the frequencies, what happened. First of all, the radiation, the power emitted per unit length. Okay, so this is the intensity. The intensity is basically how much power was emitted per unit area. So the units clearly for this intensity are going to be in watts per meter squared. So the intensity was noted to be proportional to the fourth power of the temperature, where sigma was a constant. Sigma was equal to, what is the value for sigma? 5.6 something, 10 to the negative 8, I think, or something like that. Yeah, 5.67. 0 times 10 to the negative 8. Let me be careful with the units. This is in watts per meter squared, so it's watts per meter squared. And then you have to kill this Kelvin to the power 4. So you need 1 over Kelvin to the power 4. So this is the constant, okay? This is became known as Stefan Boltzmann law. So in other words, when you heated that material and you gave it a temperature T, it's going to radiate energy, and it's going to radiate it at this rate. Okay, no matter what the temperature is, all the temperatures are going to do that. Another analysis of this same phenomenon, because you can measure the frequencies. Since you can measure frequencies, you can find the intensity of each frequency, how much you have in each one of them, and they seem to follow this law. So if I plot this one as a wave in terms of the wavelength, it depends on the temperature though. So it's going to look like this. For short wavelength, high frequencies is going to be low, then it's going to increase, then it's going to start to decrease again. And there is a maximum value for the frequency lambda m that seems to shift depending on the temperature. So this is for T1. For another temperature, again, low frequencies, then it's going to max, then it's going to start to drop. So this is for another temperature T2, where lambda m is different. So this is lambda m for the first case, and this is lambda for the second case. It seems like the second law says that the wavelength at max times the temperature, when you do this experiment, is a fixed number, 2.90 times 10 to the negative 3. Again, the units are meters Kelvin. Okay, so make sure I have the correct value in here. Yes, 2.9010 meter Kelvin. So it doesn't matter what kind of this is a black body. This is an ideal material. It's like your PV equal to nRT, basically, this expression, okay? These two expressions. Okay. Lambda m is the maximum, the peak of this function. Okay, this function is called I sub lambda. And I sub lambda is your intensity per unit wavelength. So this is your they call it emittance, and it's your intensity per unit wavelength. What I mean by that is that then I sub lambda, d sub lambda is that. So if this is your delta lambda in this range, then the power that is going to be emitted per unit area is just going to be I sub lambda times delta of lambda. So that's basically that area that you're measuring in that. Okay. The entire I, though, for the entire spectrum is going to be just the integral from 0 to infinity, all the wavelength that you can think of. I sub lambda is I sub lambda. And that is that expression that depends on sigma times t to the power 4. This entire area is equal to sigma times 10 to the power 4, depending on what t you're talking about. For T2, this would be sigma times T2 to the power 4. For T1 is going to be sigma times T1 to the power 4. So again, these are observations from the experiment. And the maxima always satisfy this relationship. This relationship is called the Wien or Wien, depending on who you ask, displacement law. Basically, the higher the frequency, the higher the temperature, the lower the wavelength, or the higher the frequency. Okay, we're taking everything in terms of wavelength in here. Okay, so this were well-known laws. Okay, so in other words, if you know, for example, the peak frequency, the peak wavelength for a star, you can find its temperature. Sorry, if you know the peak wavelength, which is meter Kelvin, divided by that lambda max. If you know it, you can find the temperature of a star. Isn't this amazing? Without going to a star, you can measure its temperature, surface temperature, just by looking at it. Okay, just looking at the spectrum, doing a spectral analysis, and see where the maximum value, where the most intensity is. Is it in the bluish color? If it's in the bluish color, that means it's shorter wavelength. That means the temperature is higher. If it's in the reddish color, then in this case, it's a longer wavelength. So it's going to be then lower temperature. So without visiting any star, without even going to our own sun, we can find its surface temperature using this law, okay? Because this is an experimental law and it really works beautifully. So this is an amazing, powerful thing. It's really very, very powerful, okay? And since I can find where the temperature is, I can go back and find what the actual light that is coming from it per unit area. I can find the luminance of that star, how much power it radiates per unit area. And if I see and find how bright it is it dim or is it bright? That depends. That's going to give me how far the star is. This is amazing stuff for astronomy, because based on these two laws, you can find the temperature and you can find the power that is emitted per unit area. And if you don't know how far the star is, you can just measure how bright the star is versus, for example, the sun. And since you know how much the sun emits, then you can find how far the star is. That is very, very powerful stuff. I mean, you can determine distances to the star based on these two experiments in here that you do, okay? Based on these two measurements that you can do. All you have to do is find the lambda max, the peak frequency or the peak wavelength. Once you do that, you find the temperature. Once you find the temperature, you plug into this expression. Now you have found actually how much it's going to emit per unit area, but you know how much you have reached you, how much light it has reached you. So it's just divided by the big 4 pi r squared, and you're going to find the distance to the star, okay? So this is basically experimental facts when people try to explain them. And the first one who got a crack at it was Mr. Riley. And all he did was borrow the same ideas that Mr. Boltzmann has used for the ideal gas and explain the temperature that way and all of that. So what Mr. Riley thought is the following: that, wait a minute, the material is made up of electrons, because at that time they were known, and those electrons, they must have energies that correspond to the entire spectrum of the visible light, and all the light, actually, not just the visible, all of these frequencies that we're talking about in here. And he used the equipartition theorem in that case, and he found an expression for the energy that is a little bit, let me find it in here. This is basically what he found, okay? So this is what the emittance that he ended up with is being look like. It's 2 pi times C times that Boltzmann constant times the temperature divided by lambda to the power 4. This is what he found, okay? It works for long wavelength, for lambda large, but it fails for short wavelength. As you can clearly see, if lambda becomes smaller and smaller, this value becomes higher and higher. This is how his measurements, or this is how his theory works. I mean, I'm going to take T2 in here. So in here, there's a match. Then instead of going down, it's going to keep up. As you can clearly see, when lambda goes to 0, this expression blows up. So for short wavelength, for high energies, which are in the UV range, which were measurable in the laboratory at that time, we're getting this much expression that goes to like 1 over lambda 4. And this is not what we observed. There is actually the frequency starts to drop. I mean, the emittance starts to drop at the end. So there is no way that this theory is correct. So this was dubbed, was called the UV ultraviolet catastrophe. Nobody understood where this problem is coming from because his theory sounds solid. This is based on stuff that was succeeded in the ideal gas law and explaining thermodynamics and entropy and all of those calculations. So all he did was he borrowed the same reasoning from there, uses for the electron as it absorbs that photon that basically at that time there was not known for that wave of electromagnetic spectrum. So hey, this is what we get from the statistics there, and this is the expression for I sub lambda, whereas the experimentally it's anywhere but that. It fails for the short wavelength a lot. Okay, things that we were measuring in the laboratory at that time for those materials, and we're getting this curve in here. So this is a problem. Mr. Planck basically tried very hard to do that, and he tried to understand this thing also, and he did not really like very much Boltzmann analysis anyway, but at the end he was forced to it, and he made the following assumption. He said that the energy really, in order to fit the experiment, all he was concerned with is, he was a theoretical first of all person, and that is not something that you like to do. But the experiment seems to suggest that the electron energies that are absorbing these photons seem to come in chunks of h times frequency, where f is the frequency and n is some integer numbers for each and every one of them. Obviously, if I plug it in terms of the wavelength again, it's nh times, he was calling this constant h divided by lambda. The wavelength that are short, in this case, this value will be higher. The gap between n equals to n and n plus 1 will be higher for lambda that are small, versus for lambda that are big, the difference between the n level and the n plus 1 level, in this case, seem to be shorter. And shorter still if you take n very high. So for n very high, it looks like the continuous spectrum of Mr. Rayleigh can match. But for short wavelength, for high energy ones, for the UV radiation, there is a big gap. If we use the same statistics as before, for example, and let's say, for example, this has a certain population that is proportional to a Boltzmann-Maxwell distribution, which is the energy divided by KBT. That's what we did, by the way, 1/2 of mv squared over KBT. But in here, the energy is not given by 1/2 of mv squared. It's not the kinetic energy of the particles that are bouncing on the wall, but it's the energy of these electrons that are absorbing these waves, and they absorb them at this rate, which is n for the lowest level, times h times frequency, and the frequency is c over lambda times kBt, and this is the expression in the lower level. As compared to the higher one, which is at a higher energy, is going to be, so there is a constant, the normalization constant I'm not writing in here because it's going to cancel for both terms, n plus 1 times, sorry, did I put in, yeah, the minus is fine, hc over lambda kBt. So this is how the expression would look like for the same wavelength. So if I do the ratio in here, obviously the n and the n cancel. So the ratio of these two terms is going to be plus hc over lambda kBt. In other words, if lambda is very, very small, this exponent is very large, and there is a difference in population between the electrons at this level and the electrons at this level, most of them are going to be here. Okay, by this exponential factor versus this ones. So the excited ones are very left. Obviously, that depends also on the temperature. So if lambda is very small, all I have to do is raise the temperature enough so that to excite some of them and move them up. Okay, but for the same temperature and for two different lambdas, one that is small and one that is large, then in this case, when it's large, this exponential is small. So the ratio between the first and the second excited state are not much difference. And then you can have, for the same temperature, of course, you can have more electrons absorbing more radiation in here. And that is a fit for this theory. That is what Mr. Rayleigh was computing, a continuous spectrum. So it's going to behave like a continuous spectrum for long wavelength, but it's not going to do so for short wavelengths. So if you follow his reasoning, basically, and it's a long one, so it's not even mentioned in the book in here. But the point being in here is that the expression that he came up with, I sub lambda, depended on that parameter h that he introduced in here, that constant h that he introduced in here, to separate the different levels of energy for the electrons inside the material to absorb only those frequencies in the case of the absorption spectrum, or emit those frequencies for the case of the emission spectrum. So the expression that he came up with, it's really a, it's 2 pi, depends on that h parameter again, 2 pi times h times the c squared in here. Again, c is everywhere in this expression, divided by, I'm going to just copy it in here, lambda to the power 5 times the exponential of the energy gap difference, which is exponential of lambda kBt, lambda kBt, not lambda bkt, minus 1. Okay? So this is the expression that he came up with after doing the statistics, because it's really a long argument using statistics, and we really didn't cover much statistics, honestly, in this class. So this is the emittance that he came up with. This agrees with this expression for long wavelength, and it accounts actually for the short wavelength. It's a match actually between this one and the experiment. Experimental physicists, they were ecstatic when they saw this expression because it matches beautifully. Let me clear this section here because it's kind of a lambda kBt. Okay, so that's in the exponent, by the way. So it matches, but he himself and theoretical physicists, they didn't like that at all. Where in the world this come from? I mean, it explains the experiment. It comes up with an expression for both sigma and this term in here, this constant, beautifully, because all you have to do is take d sub I with respect to lambda and equate it to 0 and find lambda max, and it's going to give you that expression. I think that's one of the homework problems. And then also you can integrate this expression and you're going to get that constant. So all you have to do is integrate I sub lambda d lambda from 0 to infinity, and you're going to get something that is proportional to t to the power 4, and that proportional term is exactly 5.670 times 10 to the power negative 8. Okay, so everything matches, where that constant has to do with kb and c and h and all of those terms in here. Okay, everything matches, and he himself did not really have any justification for what, other than the fact that it matches the experiment. Okay, and there was no, and that's what Einstein later on used for the photoelectric effect, and that's what Compton used, and that's what Louis de Broglie used, and that's what everybody later on used, and it seems like it's working like magic, except there was no justification for it. So really, he himself, in one of the letters, he said he was kind of basically apologetic. My hands were basically forced to introduce that constant. That's basically how he saw himself doing that. And like I said, everybody later on was happy with what he did, including at the end, he won the Nobel Prize in 1919 because of this thing that he did. Okay, so that is why it's called Planck's constant, and it's coming everywhere in all of the phenomena that we came in up to here. And it seems like even at the quantization level, everywhere. So this H in here, which turned out to have that value, now we know it's going to be equal to 6.626. times 10 to the negative 34 joules second. This is a constant that he himself introduced, like I said, and at the end became known as Planck's constant. So this is the black body radiation, as opposed to the emissions that we were talking about earlier today, namely the atomic level of absorption, which are lines basically, or emissions which are lines or missing lines thereof. And in here, you're talking about continuous spectrum for the black body radiation. And it's really this theory in its full-fledged. The last part of the chapter really deals with what I mentioned before, and that is the Heisenberg uncertainty, because now since particles are behaving like waves, they too also give you delta x times delta p greater than or at least equal to h bar over 2, where each bar is the same h divided by 2 pi. And also delta t times delta E is greater than or equal to h bar over 2. This x and this p are corresponding to one another. Okay, you cannot have a py and a delta x in here, or you cannot have a delta y and a py in here. They have to be in the same. In other words, this is delta y, delta py greater than or equal to h bar over 2, and delta z times delta pz also is greater than or equal to h bar over 2. Okay, so those are the Heisenberg uncertainty, and they work both ways, in both directions. Okay, so it seems like particles behave like waves and waves behave like particles. This is the deal that we are coming from chapters 38 and 39. So the duality is anchored solidly now, okay, is real for both, in both ways. Particles behaving like waves, now we know that from chapter 39, and vice versa, waves behaving like particles from chapter 38. Okay, let me make clear distinction about the two. Do you guys remember your standing waves from physics 1 and the equation that led them to them? Yes or no? I'm asking. Can you guys hear me?
Yeah, I think I remember that. Sorry, I was browsing through some notes.
Yeah, basically, how's everybody else doing?
Doing good, I'm here.
Okay, so let me go back into the screen in here and talk about that question. So if you guys remember, you have a string and it was sitting under tension. So there is tension on the left and there's tension on the right. The tension on the string is the same. So this is kind of a string in here from here to here, okay? And that is the tension. So what you do in this case, you break down the tension, it's a vertical component, and it's actually a vertical component, and it's a linear component, and this component this way, and that component and this way. And you end up with a displacement, which is on the y direction, and this is the x direction, and the time is the factor between them. And you will end up with an equation for the wave that looks like this. 1 over velocity squared times the derivative of the displacement with respect to time. Is this equation you ended up with? Do you guys remember vaguely? I know that some of you
Yes.
took it a long time ago. Yeah, so this is the wave equation. Once you reach this equation, you call it a wave, because the solution y in this case is going to be two solutions, the outgoing wave and the incoming wave. Okay. And for harmonic solutions, actually, for cosine and sine waves, it's easy to write. So let's take the outgoing. For the outgoing, it's going to be cosine of, because this is x and this is in meters and this is in meters, we really need to have something to cancel the meters. So we're going to call it kx minus vt, or we can write it as k, where k has a units of 1 over meters, minus vt, in this case, we have time, which is in seconds. We use it as omega t. Well, this is a cosine. I could take a sine. I could take any combination. I could take a phase difference in here. So the main thing is this is the behavior in space and time. I know that there is a scaling factor here for the amplitude, but that's basically what the harmonic wave would look like. If I take this expression and take its derivative with respect to y, with respect to t, for example, I'm going to pull a minus omega from this expression times the sine, which is a sine of kx minus omega t. Oh, I'm sorry. That is, when I take the derivative of the cosine, it becomes a positive, it becomes a negative, so the negative times the negative is going to be positive. So it's going to be an a omega times sine of omega t. If I take the second derivative with respect to time of this expression, I'm going to put a minus omega, the sine become a cosine again. So it's going to be a cosine of kx minus omega t. And the minus that I pull times this omega becomes a negative omega squared. So we have an omega squared in here. If I take the same derivative with respect to x is going to give me, I'm going to pull a k in here. The cosine flips to a negative sine, so it's going to be a negative a times k times sine of kx minus omega t. If I'm going to take the second derivative with respect to x, is going to be, again, I'm going to pull another k, the sine flips to a cosine, the negative stays intact, so it's going to be minus k squared times a times cosine of kx minus omega t. I plug them back into the wave equation, which is here. So what this expression looks like then is the derivative with respect to x is k squared with a negative sign times the a times cosine, where the a is the amplitude of the wave times cosine, the harmonic wave in this case, must be equal to 1 over v squared times derivative with respect to t. So this must be equal to negative because I have a negative sign in here. Again, omega squared over v squared is equal to a times the cosine of kx minus omega t. I'm going to get the same result even if I use the sine or a combination of both of them. So this cosine cancels, the a cancels, and the minus cancels. So what I end up with is omega squared is equal to k squared v squared. Okay. This is, by the way, the dispersion law that we used in electricity. So this is a dispersion law. Omega is always positive. So when I take the square root, and k is always positive when I take square root, and v is the speed of the wave. Okay. And if you care to take the plus or minus, then the minus will be here, and you're talking about the outgoing wave. Okay. So that's both of solutions are going to give you the same result. So this is the dispersion law. In our case, the frequency omega and angular frequency are related by this relationship, and k and the wave number are related by this relationship. So basically what this expression look like then is 2 pi times the frequency is equal to 2 pi divided by lambda times the velocity. We cancel the 2 pi from both sides, move the lambda to the other side, and lambda f equals to v. This is the dispersion law for all waves. For the case of light, we've been using all along lambda f is equal to c. And that is because if we do Maxwell's equations from chapter 32, all you have to do, you end up with the electric field in here, its derivative with respect to x is equal to 1 over the speed of light squared, which is really, and from chapter 32, if you guys remember, c is equal to 1 over square root of mu naught epsilon naught, where permeability and permittivity of the vacuum are going to be exactly equal to c when you put them in the square root. And this is going to be the derivative of the electric field with respect to time. You do the same thing with the magnetic field, you're going to get the same equation. So this is whether we do it on waves on a string, or waves on for the electric field, or waves for sound, or any waves you like on the surface of water, any waves, you're going to end up with the wave equation at the end of the day, where v is going to be the speed of that wave. Okay. For the case of light, it's turned out to be exactly this value, which is the speed of light, 300,000 kilometers per second. And that is the value that we've been using all along. And this is a dispersion law, as I was talking all along. So in terms of wave number and angular velocity, this is the expression that we really want to use. Okay. This is coming from this equation. However, for a free electron, for example, what I mean by free electron, I mean an electron not inside an electric field, and not inside any, it is not subject to any forces, okay? It's moving by itself. It has a wave number lambda that is equal to its energy divided by, I'm sorry, it's equal to h divided by its momentum. This is basically what we have found, okay? And This is one expression between the wavelength and the momentum. Furthermore, the kinetic energy for this particle is going to be equal to h times the frequency, and the frequency is related to the velocity by 1/2. We're taking the classical, okay, classical free electron. So it's free. It's not inside any potential energy. So the only thing that it has is a kinetic energy. End of the story. Okay. Let's think about this expression for a moment. The frequency is related to omega by this expression. So I can write this expression as being also divide by 2 pi and multiply by 2 pi. If I do that, this is going to be omega and this is going to be h bar. So this is omega h bar must be equal to 1/2 times mv squared. Now mv squared also I can write it in terms of p. Remember, p is equal to mv. So in this case, if I square this expression, I'm going to have m times mv squared. Okay, so the same thing. All I did was square this expression. So the kinetic energy in this case is going to be, which is 1/2 of mv squared, which is the total energy in this case completely for the system, because it's free, is going to be 1/2. It's going to be p squared over 2m. All I'm doing is just moving the m to the other side and write it in terms of the momentum. So in terms of the momentum, this is the energy that I'm dealing with, is p squared over 2m. I'm sorry, the 2 is already here, okay, over 2m. So this is the energy that we're dealing with in here. Well, from this expression, p is equal to, again, h over lambda. What I'm going to do in here, I'm going to do the same trick, divided by 2 lambda and multiply by 2 lambda. 2 lambda over 2 pi over lambda is your k. 2 pi over lambda is your k. And h over 2 pi, that is your h bar again. So this is your h bar k. So that is actually the momentum. If I plug it into this expression, this is the expression I'm looking at then. Omega h bar, that's the energy. For a free electron, there is nothing else in here except the kinetic energy. So it's going to be h bar squared k squared divided by 2m. Unlike this expression, which tells me that omega, what is it, equal to kV, this expression tells me that where k is the wave number. So omega and k are linear relationship. So this is a line for all the waves. Okay. So if this is k, this is omega, this is a linear function where v is just the slope of this line. Here, it's not linear anymore. You can see that omega is proportional to k squared. Yes, quadratic in k.
Yes.
Okay, so the wave equation that we're dealing with, honestly, is not this wave. This is what you've learned from physics 1. This is what you learned from physics 2. This is what you learned up to this point, and it always leads to a dispersion law that is linear between the wave number k and the angular frequency omega. We need an equation that has an omega. Remember, omega comes from the first derivative with respect to time. We drop an omega. And omega and k squared comes from the second derivative with respect to x. So we need an equation for the wave, for the electron, in such a way I'll have the derivative with respect to time, and I will have the second derivative with respect to x. That is going to be my equation that I'm going to have. So this is what we will need to do in chapter 40. So this is the setup. We need stuff in here to fill in the gaps. Obviously, we need to work. So h bar over 2m in here, and this is something that has to do with h bar. It turns out I will come into play. Remember your I from your square root of -1. And this equation is what is known as Schrodinger's equation. We'll find it for the free electron and try to fix it. because remember the term that's going to appear in here is going to be equivalent to the kinetic energy. So we need to add a potential to it, so that then we will have the entire wave equation for the electron that is not free. I mean, electron that is bound to a hydrogen atom, for example, or even to the helium atom, and we can find whatever we want to do later on and solve all of those stuff for the spectral lines and everything that we talked about for the atoms. You guys see the setup for the second part of this class, or the third part of it?
Mhm.
Thank you, Cameron. Let me re-emphasize where we are from classical physics. Whether we're dealing with F equals to ma that led to this equation for the standing waves on a string, or sound waves where V turned out to be the sound waves, or even for the electricity and magnetism, where we have the electric field and the magnetic field coming into this wave equation, we ended up with a dispersion law that is linear between the wave number and the angular frequency, where the constant of proportionality is just the speed of the wave. Here, we're talking about an electron that behaves like a wave, or a photon that behaves like a wave, or a wave that behaves like a particle. But it seems like when they are free, when there is no potential, the relationship between the wave number, k, and the angular frequency is not linear. It's quadratic, okay? So our challenge then is to find an equation similar to F equals to ma, if you wish, that is going to set up the stage for everything else. And that equation is what is known as Schrodinger's equation, okay? Once we find it, then we are in business. Then we can fix, because this term is coming just from the kinetic energy, that's all. Then we need to fix the kinetic energy to account for the fact that it's not necessarily free. It can exist in a potential, okay? Once we do that, then we have an equation that should fix all the problems that Mr. Niels Bohr failed to do with his theory, and should do also the hydrogen atom too. We should be able to get the hydrogen atom, including that principal number n. So this is the plan for next. Basically, we're making a huge jump in here from the classical physics to a brand new physics called quantum mechanics. Okay. So let me first jump to the lab, because I think it's going to be fun, this lab. I already opened the page. I think I did. So I'm going to stop sharing. Any questions about the electroverse and stuff that has to do with these concepts? You're good, everybody?
Yep, I'm good.
Okay, so let me jump into the lab, as I was saying. First, we'll find it. The instructions on this lab. Does everybody see this fat link from Colorado?
Yeah, we can.
Okay, when you go into this website, they changed the website. This is the only thing that is different. In such a way, they ask you to donate. So if you want to donate, donate. If you don't want to, you can just skip that part, okay? Then they ask you, do you want to download the Java file or use the web version? If you don't have Java installed, and I don't mean JavaScript, I mean Java, the actual programming language, okay? If you don't have a Java installed on your computer, there is no point of download the Java file. And you just go to the web version. So please use the web version, it's going to work fine. If you want to work with it offline, you can download it and work with it offline using Java. Java opens something called a Java applet and starts working with it on your computer, and you can do all of the simulation using that. People don't recommend Java usually because of the fact that it opens a new thing in your computer, and historically it was known to cause problems. I know some of the labs ask you to do that in Java. When you're done with it, I think you should remove Java from your computer, especially if you don't know, if you don't have a lot of expertise with these things. So remove the thing, or turn it off completely so that it doesn't work on its own. Okay, for security reasons, that's all. Anyway, so these are the changes. The only changes, as I was saying, they ask you to donate, and then they ask you to, when you click on it to open it, do you want to download it or do you want to use the web version? Choose the web version. Other than that, the lab asks you to change the intensity from up to 50%. Right now it's very high. Right now it's very low. So they ask you to raise the intensity to around 50%. Okay. I got it earlier correctly now. Okay, 50%. And also you change the wavelength until you see it starts to emitting or stop from emitting radiation electrons. Right now I see electrons coming. So if I stop it, now I still have electrons coming. If I change the wavelength to longer wavelength, I still see it coming. So right now it's in the visible range, okay? And this material is sodium. So I'm going to change this number down to a longer wavelength until I see no emission of electrons. Okay. Do I see it at 552 nanometers? Doesn't look like I do. When you're doing this, you have to be careful. It doesn't mean that 552 nanometers is the correct answer, okay? It means that probably it's 551. How about if I go to 541? Do I see any emissions? No. So it's shorter than 552, definitely. How about if I make it 527? Now I see it, okay? So I have to move it back to a little bit more until I find the point where there is no emission of photons, of electrons, I'm sorry. So this is the photoelectric effect. So I'm getting, so 538 is no good. Okay. So you guys understand what you're doing in here? Try to use the cursor, okay? I cannot use the cursor. Can I change the value manually? Yes, I can. So that's good. Then change it to 540 and see what it does. Click out of it. So 540 kills it. 539.
What are you looking for, DJ?
I'm looking for the cutoff frequency where there is no electrons coming.
So you're looking for no electrons.
Yes. At this point, if I drop it to 540, it seems like I kill all of the electrons. So if I put 540 nanometer, you see the electrons? You guys are looking at this animation or not? First of all, am I sharing
Yeah.
my screen or?
Yeah, we are.
It seems like at 540 nanometers, I see no electrons coming. So that's what I'm going to record for sodium for this intensity in here, okay? And it asks you to turn on the graphs and see what you have to see and so on and so forth. Then yeah, at some point, you're going to change to different materials, okay? Copper, platinum, and each time you notice the difference of the color in there, calcium, and so that's basically what the lab is. You can change the intensity in here. You can change the voltage, okay? That's to accelerate them more, okay? So this is the stoppage voltage now to kill them. Do you guys understand that the simulation is easy for this lab? Yes, no, maybe?
Yes.
So all we're trying to do is just find the right wavelength where there's no electrons, where there's no of these blue dots coming through, right? That's it.
That is for the cutoff. There is more spaces to it. There is more stuff to it. You at some point it's going to ask you to increase the frequency, meaning you have to make a shorter wavelength.
Right.
Okay. If that's the case, you're gonna definitely I changed the material. Yeah, back to sodium. Now I'm using a negative voltage. Do you see it? So at some point it's going to ask you to change the voltage until. Do they make it with this voltage? They do. It's a positive, of course they do. Okay. It has to be a negative too. Stop them. Okay. So follow the instruction of the lab. The point I'm trying to show you in here is the entire animation is kind of it should be straightforward for the most part. Okay. It seems like this voltage of negative 0.2 volts stops them before they reach the anode. Okay. For this part. Okay, there are a lot of questions in the lab. I want you two guys to go through them step by step, but just to show you the animation itself is not hard to follow. Sounds good?
Yep, sounds good.
Yep.
Okay, So if you guys have difficulty with it, please let me know, because the only problem, as I was saying, with respect to the instructions that are missing from the instructions are the fact that there is the website has changed in a sense it asks you to donate. And I would urge you not to donate right now. Donate some other time when on your own time if you really want to donate, okay? That is one thing. And then it asks you to download the Java file or run it on the website, please. That's it. And then once you're exactly in the picture that I am looking at. Good.
Yep, sounds good.
Yep, sounds good.
Okay, so let me close that thing in there, because I really don't want to share with you the actual instructions. Again, this is the website. Don't forget your name. I noticed something that some of you are using the not in the proper order. If you are the one who is graded, your name should be first, and everybody else should be after you. It doesn't matter who, but your name should be first, must be first, and then the name of the other people behind you. Okay. Please read the background and read the lecture, and come back to the lecture if you want to, and read the book. And the objectives try to focus on the experiment itself, the concepts that are covered in here, the stoppage voltage, how the frequency and the stoppage voltage are related, and all of the concepts that are covered in here. Try to be as brief as possible and don't use formulas if you can. If you can't, then that's the only way to express it, that's fine, okay? Then answer briefly the questions that you have in here based on that background, okay? And this is the link, as I was saying in here. You click on it, it takes you to that link from the University of Colorado. And you have to be careful, mindful of the two issues that came up. And then in here, for different materials, you're registering wavelength. The wavelength is given to you in nanometers. Use the dispersion law, which gives you the frequency. Frequency is equal to C over lambda. So from there, you're going to find the frequency. Multiply that by H to get the energy in joules. H is 6.626 times 10 to the negative 34. And divide that number for the energy by 1.602 10 to the negative 19. You're going to get the expression in electron volts. And you do it for different materials. They're all listed in the animation in there. And then the threshold frequency, where you start to see, that is what you need to record. That's the one I was simulating actually, is to kill that, to change the frequency, to change the wavelength until you see no current. I think we found it 540. Please verify it on your own for sodium, but you're going to find it for the other materials also. And you're going to use the algebra to find the work function, both in joules and in electron volt. Okay. The work function and the threshold are related through this expression, so it's straightforward, really. All you have to do is multiply that number by H, and here is your H. And both actually in joules and electron volts. So on this side, you multiply by this number, on that side, you multiply by the other number, and you're in business, so it's really not hard. Then you answer the question, and then you're going to graph the electron energy versus the frequency, and you note the graph that you're going to get in there. Okay, and what is the number of the what affects basically on the number of the electrons as you increase the intensity, and at the end you're doing the conclusion. Isn't this an easy plab? I don't think that you can get it easier than this. Sounds good?
Yep.
Okay, it doesn't mean that you're not gonna run into difficulty. Please, if you do, let me know, okay? I really don't want you to have problems with it. I don't want you to feel shy that maybe because it's easy, maybe if I ask a question, maybe he's not, no, okay? If you run into some difficulty and you would want to have it perfect, please let me know so that we can fix whatever needs to be fixed, and then we'll proceed, okay? So I'm gonna close this one in here. Are you guys in the mood for a couple of problems? Yes, no? The person who's going to say yes probably is going to be killed by the rest of the classmates later on.
No, I'm never in the
Natasha, are
mood.
you? No, I am. Okay, so
Aren't you tired?
the
It's been
person.
like
Well, let's. I mean, look, it's fun, okay? When you do things, when you're having fun, you never get tired. Aren't you guys having fun too?
oh yeah,
I'm
definitely.
having so much fun.
So am I.
A ton
I
of
love
fun.
taking notes.
Okay, let's get at least a couple of problems because we really have to get these ideas hammered in. Otherwise, we'll have difficulty doing problems and things like that. So we really have to do these things. Sorry. We'll spend maybe let's see how it goes. Okay. Hopefully you guys have the book. I'm looking at chapter 39. Okay. And probably I'm going to jump back to chapter 38 too, because we didn't do any applications from chapter 38. So here is the deal. Problem 60 from chapter 39. Problem 62 from chapter 39. Problem 70 from chapter 39. Problem 71 from chapter 70. Problem 39. Chapter 39. 71 from 39. Okay. And 83 from 39. Okay. I'm going to jump right into 62 because it has ideas from relativity and stuff like that. So I mean, from optics actually. And then we probably are going to jump back to chapter 38 and talk about a few problems from there. Problem 59, by the way, from this chapter is straightforward answer for you. It's just using the okay, what did you say, Natasha? I said 60, you're right, 62. 71, I didn't say 72, unless you want to do 72 too. Natasha.
That's okay.
72, by the way, we're going to come back to these similar problems later on when we get into chapter 44 and so on and so forth. And then I said 83, you're right. I didn't say all 39. Do you want to do all of them? That sounds good, actually.
No, I'm at like
Okay.
chapter 39.
59, I said, is fun because of the fact that it's pure calculus, integrations, and doing derivations and things like that. And that has to do with that, with the black body radiation using Mr. Planck's basic expression for the emittance, and we're done with it. So, okay. Actually, in the past, we used to do that in the classroom. Problem. So, problem 62. Am I sharing my screen? No, I'm not. Share. 62. A lot of these problems, as you look down into the videos, you'll see them, you see me doing them. And basically, if you find difficulty or issues with those, please let me know so that we can fix them. So problem 62 from chapter 39 says that an electron go through a single slit of 300 nanometers. So A is 300 nanometers. Okay. And strike a screen 24 centimeters away. By the way, 24 centimeters is infinity compared to 300 nanometers. It's the other side of very far away. Okay. So that's where the screen is located. So obviously, since this is a single slit, the central fringe is going to be super bright. 85% of the radiation is going to be the central one. Then there is a dark fringe. Then there is a small bright fringe, then a dark one, then bright fringe, and so forth. If it is a wave, because it's an electron, it's a particles, and it behave like waves for our case, okay? So the central region is going to be super bright. And this is located, the first dark fringe is located at 20 degrees. So this angle is 20 degrees, okay? So this distance is some distance, and here on the screen. So this is where your screen is. Okay. From the center of the different at the angle of plus or minus, of course, because by symmetry. So this is a minus 20 degrees. No electrons hit the screen. So anything above or below, there is nothing in here, okay? Wait a minute. No, I'm sorry. What am I saying here? I think you're right, guys. I'm getting tired. There is no electrons in here. So there are electrons in here. They're in here. No electrons in here. There are electrons in here. They're in here. Make sense? Yes.
Do it again, just to be sure.
Okay. This is the spectral lines from physics 2, basically, when you're dealing. So this is how the screen would look like. The central fringe is here. It's bright. So this is the center of symmetry. So this is where the electrons are going to be. So this is the central fringe. Then there is a dark region, no electrons in here. Then followed by a bright region where there are electrons in here too, followed by dark region, followed by another bright region, and so on and so forth. And by symmetry, there is a pattern that is going to be in the bottom also. These two are the same size. They should be like this. The central one is super wide, that's all. So this is the single slit experiment. Single slit experiment. Do you guys remember this when we did physics 2?
Yeah.
It was the interference pattern, right?
So this is your single slit. Sorry? Can you repeat it?
Wasn't this is the interference pattern?
Yes, this is the interference patterns that you did from physics 2. There were 2 experiments. There is a single slit and there is a double slit. In the double slit experiment, the patterns are a little bit more regular than this. In the double slit experiment, again, the central is bright, followed by dark region, followed by bright, followed by dark region, followed by bright. And the same thing is happening in the bottom. The only difference is basically, so this is the central. In the double slit, the spacing in here and in here and also is uniform, and in here it's non-uniform. The central region is brighter, and the single one in here, the double slit in here, so this is the double, is uniform. The single slit has this pattern. As a matter of fact, I don't know if you did this or not in the actual lab. If you were careful enough, you could see there are lines in here that are brighter than others in here. And they're uniform. And there are cancellations in here. And then the same pattern repeats in here. And the same pattern repeated in here. Those are the double slit. I mean, I'm sorry. Did I make this one? That's stupid. That's stupid what I just said. Here. You see them in here. You don't see them in here. You see them in here. Because when you did the double slit, it's 2 slits that are open. The spacing between them is A. I mean, the openings are A, but the distance is D. D is very large compared to A, but you still see A inside. Okay? You still see A inside. But when you do it in here, there is no D in here. So the effects of A are going to be in here, embedded into this code in here. Okay? So that's something that you probably have dealt with when you're dealing with physics 2. But the point being in here, ignore this. We're doing a single slit for this problem. This is how the pattern comes in. And it's interference. You're absolutely right, because of the fact that electrons now are behaving like waves. So somehow they cancel each other, which doesn't make sense because they are particles if you think about it, at least from classical perspective. But now since they are waves, they really do behave like this. Okay? And that's exactly the experiment of Germer and that really proved this one. Okay, so this is the setup for the problem. Everybody is good on it?
Yes.
Okay, they tell us how fast the electron, were these electrons moving when they went through the slit. We want to find lambda. Once we find lambda, we can use this expression P equals to H over lambda. Once we do that, P is just MV or gamma MV if it turns out to be moving too fast. So depending on how that expression is. Okay, so this is really the expression that we'll be using. So we're going to use MV and see what V will turn out to be. If V is very small compared to the speed of light, we use MV. So that is basically the expression. We know M for the electrons. It's 9.1 times 10 to the negative 31. So we need to find lambda. For the interference, for the single slit, if you guys remember from physics 1, destructive interference will happen in here in such a way that A times sine of theta is equal to n lambda or m lambda. Actually use the letter m, but I'm using n in here because of the fact that I already have m for the mass in here. But you used m, I remember you used m in here, where n is the first dark fringe, or dark fringes in dark fringe, where there is cancellations of the interference. Okay, n equals to 1 is the first, actually. N equals to 2 is the second one here. N equals to 3 is going to be here, or -1 is here, and -2 is here, and -3 in here. Make sense? Because this is an integer.
Yeah.
Okay. I should have been careful earlier for the quantum numbers when I mentioned the fact that they are integers. I meant positive integers for the energies when we were doing the hydrogen atom. That n for the angular momentum was a positive integer, so we could not use them as negative numbers. But in here, you could use positive or negative for this one in here, because your spectrum is going to be up and down. Okay, symmetrical with respect to the central region. So n can be positive or negative in this case. And it's just count for this dark fringes. That's how we find them. And the bright fringe is going to be anywhere between those. So for n equals to 1, we know that A sine theta is equal to lambda. So this is the first one. And that's the one they tell us happens at theta equals to 20 degrees. Okay. So they said in the experiment that at that theta, there is cancellation. There are no electrons that are going to be recorded at that location. Since we know A to be 300 nanometers, all I have to do is multiply by sine of 2, and then I have lambda. If I have lambda, do you guys agree that I have the velocity of the electrons? Namely, the velocity is going to simply be equal to h divided by the mass of the electron times, again, just to make sure that this is not an integer, this is just a mass of the electron, times lambda, and lambda, we know what it is now. It's coming from this expression, which is 300 times sine of 20 degrees. Yes?
Yes.
Anytime you find a velocity like this one, you need to check versus C. Is really V too small compared to C? If it's not, you need to fix the momentum, yes. Okay. So that is typical behavior. So you need to be mindful of the fact now, anytime you have a velocity compared to the speed of light, otherwise you have to fix your mechanics that led to that expression. Okay. What will be the next pair of angles? So basically, what is for n equals to 2? That's all. So we need to find theta when n is equal to 2. That's all. So in this case, A times sine of theta must satisfy 2 times lambda. And lambda is given by this expression, which is A times sine of 20 degrees. So that is what lambda is. So from here, we're going to find theta equals to arc sine of 2 times, when you cancel the A with the A, it's gone. Okay, so the A doesn't matter anymore. Sine of 20 degrees. You have to multiply 2 times the sine, and you find the arc sine. So you really have to be careful with this expression here, especially if you have a calculator that doesn't do degrees. So you have to make sure you convert this back to degrees to see if it makes sense, if it's still within 0 and 90 degrees. Because if you find an answer that is going to exceed 90 degrees, that means it's an infinity. Okay. So if you find 112 degrees, for example, from this calculation, or some nonsense numbers in here, you have to be careful with it. In other words, you have to make sure that this whole number is less than 1. If sine theta has to be 2 times sine of 20 degrees has to be less than 1. So at most is equal to 1. That's it. That's 90 degrees. It cannot be more than 1. Does this make sense?
Yes.
What is theta? I understand it's an
Theta
angle,
is the-
but like what angle?
So the first angle that we measured was 20 degrees. We want to find this theta where n is equal to 2.
Oh, okay, I understand.
Okay. We want to find theta equals to 3, so we're going to plug in 3 in here. So that's the other theta. Okay.
Okay.
Yes. So those are the dark fringes that satisfy this equation. You slit, because at some point there will be no more light. That's it. You reach the time maximum theta that makes this expression, because for any subsequent theta, so this should really be called theta 2 now, and the first one will be called theta 1. So any theta of index n will satisfy the arc sine of n times sine of the first one, in this case 20 degrees. Okay, this number has the potential to be more than 1, has the potential to be big for n large, and you cannot have a sine that is bigger than 1. Sine is always between -1 and +1. Sine of any angle is maximum is equal to 1. So in this case, this is the maximum pattern that you're going to see on the screen. After that, you're not going to see anything. Make sense?
Makes sense.
Okay, so that is actually from physics 2, honestly. But the point being in here is we're finding the second dark fringe, the second point where all the electron waves cancel, and I don't see any electrons in that point. Okay. Yes.
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 Okay. Problem 60 is a combination of a double slit No, actually, it's a single slit also. It's a single slit, and also and the dispersion and and Heisenberg principle, because at some point you're going to calculate the value for delta p in the y direction, how much the momentum has changed in the y direction, and you find the delta y in the y direction, but the delta y you're going to use the Heisenberg relationship, which means that delta y at most, or at least, I'm sorry, is equal to h bar over 2 times delta py. Okay, so that is for that problem. The problem 64, which I didn't tell you to do, but it's actually you have the potential of having stuff like this one in exams, because once you do the single slit, you can do the double slit. Okay. This problem 64 is for a double slit. Coherent light is passed through 2 narrow slits whose separation is 20 micrometers. The second order bright fringe is an interference pattern is located at an angle of 0.03 radians. So the angle now is given to you for the second one. Okay. But that satisfies a similar condition. Let me set up problem 64. Natasha, add 64 to your list, okay?
For sure.
So here, okay. So what you have a D. I'm sorry, I can't draw this. So this is D. So you have basically where this is light, okay? This is chapter 38 though. This is not. I know it's chapter 39, but now the ideas are the same. So you have photons actually now, light, photons. that are going through two slits in here for the double slit experiment now. Okay, so coherent light is passed through two narrow slits whose separation is, so they gave us D to be 20 micrometers. Okay, the second order fringe. So now the interference patterns, they're constructive. So we're looking for the constructive patterns in here. So the second bright fringe, and the bright fringes are satisfied as sine theta is equal again to that n from chapter 36, we use the letter M times lambda. So this is constructive versus the other one, which is destructive. So this expression is for destructive, and the only one we have for the single slit, if you guys remember, remember from physics 2, is just the destructive patterns. It's not easy to find constructive patterns. In here, you can find constructive patterns satisfying this condition, and destructive patterns in this case satisfy another one, which is d sine theta is equal to n plus 1/2 times lambda. So this is where dark fringes, and this is where bright fringes are. Okay, this is from physics 2. This is nothing to do with physics 1, physics 3. I'm sorry. Anyway, so in here, the second brightest point, because that means n is equal to 2. Okay, and they gave you the angle theta, 0.03 radians. Okay, and basically now you can find lambda. Do you guys agree? Yes.
Yes. You just set them equal to each other?
Yeah. D times sine of 0.03. Make sure you're using the radians, though. Otherwise, you're going to get the nonsense inference if you use the degrees, or convert that to degrees and use your calculator normally. Equals to 2 times lambda. From here, you should be able to find lambda. Okay. If electrons are used instead of light, what must be the kinetic energy in electron volts of the electrons be if they are to produce an interference pattern for which the second order maximum is there? Okay, so from here, we can find how much energy is going to correspond to this frequency, to this wavelength, because the energy is going to be HF, which is HC over lambda. You find lambda from this expression, you find the energy for this photons, okay? And now if we use electrons instead, these electrons must have the same wavelength as these guys. You guys understand?
Yes.
Then in that case, the energy of these guys has to be, if it were photons, if it were electrons instead, it's going to be gamma minus 1 times mv for the protons. I'm sorry, times mc squared. Okay, if they were actually electrons. Okay, I need to find gamma for these guys, or we use the classical approach, or say it's equal to 1/2 of mv squared. I'm not sure which one works honestly for this problem. I have to try both, okay, to see if it's going to be classical or it's going to be relativistic speeds. So what I do in this case, find the momentum corresponding to that lambda. So if it were electrons, this is how much velocity they need to be moving with. Their velocity will be equal to h over lambda. I mean, the momentum is h over lambda, and the velocity is h over m gamma times lambda. Obviously, v and gamma are related, so I have really to solve this. So first approximation, ignore gamma, make it 1, okay? And find the velocity. If the velocity is significant compared to c, then this expression is no good. You guys understand?
So the
Yes.
velocity has to be less than c, right? Is that what you're trying to say?
Okay, find the momentum first, h
Right.
over lambda. Once you
Mhm.
find the momentum, equate it to gamma mv, okay, in general. Put gamma equals to 1 and work with it. See if you find velocity, this you have lambda from the first expression. Here is lambda. You have h, which is a constant. Find limit. Once you find v, is v acceptable? Is v too big? If v is big, of the order of gamma of c, or even bigger, which is worse, then definitely this expression needs to have gamma not equal to 1. Then you're going to solve this expression for the velocity, because remember, you have gamma, which is 1 over square root of 1 minus v squared over c squared, and that is equal to, and here you have mv, typically you divide by c and multiply by c, so it's mc equals to that momentum, whatever is h over lambda, and h over lambda, if you wish, you can find the expression for it in terms of the energy. So now, if you want to, this expression becomes an equation for v over c, which is beta. So it's going to be mc times beta divided by square root of 1 minus beta squared is equal to h over lambda. You guys agree that everything in this equation is known with the exception of beta?
Yes.
Yeah.
The mass of c, h, and lambda, which calculated from the previous step. Okay, so this is a quadratic equation in beta, because you will have beta times something in here times mc over lambda, mc lambda over h, I'm sorry, equals to 1 minus beta under the square root, square both sides, and you're going to end up with some constant squared times beta squared is equal to 1 minus beta squared. Move this beta to the other side, and you solve for beta, which is this quadratic equation, which is easy to do. Okay, so that's big. So again, you put gamma equals to 1, make your life easy first. Find mv. If v is very low, then don't worry about it. You're in business. Okay, you're in good shape. If v is high, of the order of c, what I mean by that is anywhere between a third or fifth of the speed of light, or higher, or even greater than speed of light. That is when you say, you put the brakes on everything and say, you know what, this method is not classical. This particle, this electron is not classical. So I better go back and find it in terms of the other one. Okay, so you have to find beta. Once you find beta, basically you find gamma. Once you find gamma, you plug it into the expression, you find the total kinetic energy that you need. Okay. Sounds complicated, but it should not. The only difficulty with it is finding this solution to this quadratic equation for beta. And I trust that you guys should be able to do this. Because once you find beta, now you have gamma, which is 1 over square root of 1 minus beta squared, which actually you could get beta squared right away. You don't really need beta in here. You need beta squared from this expression, plug it into this expression, and now you have the energy that is required for the electron. Because you really need gamma. You don't need beta. So since you have beta squared, this equation gives you beta squared. That's exactly what you need for this one. Sounds good? As a matter of fact, you need 1 minus beta squared, which is, after you solve it, you subtract from this equation and you're going to find it here. Does everybody understand how to proceed? This is, by the way, true for all problems. Okay, anytime you have a problem, especially with massive particles, and you're asked to find their velocities or momenta or something. Momentum, there is no cap on it, so you can find any momentum you like. But the velocity, there is a break on it. So anytime you find the velocity, that is when you have to ponder about your answer. Is this acceptable? If it is, then you're in good shape. If it is too big, then that is when you have to redo the calculation. So this is true for any problem. It's not just for this one. Yes, everybody?
Yeah.
See,
Somebody else was saying something other than Amr? Was it Maddie?
I didn't say anything, but this makes sense.
Honestly, the sound is coming convoluted. I really didn't understand what you said, Maddie. So I just said yes, but I hope that Good.
Yeah, I think so.
Yeah, I'm good.
Okay, very good. Okay, chapter 38. There is a problem that I must do because of that requirement for the pretest. By the way, I changed the post-test. It's no longer optional, it's required, okay? And it's great, it's going to be part of your homework assignment. So because last time, apparently when I did it that way, people did not take it. And then I was sent an email asking me how come your students didn't take it. And I explained to them, so they said maybe next time we should ask them to do it, we should require them to do it. So the post test is required now, okay? So you're gonna get a grade for it and it's gonna be going toward your homework. So it's good. So this question is related to it from chapter 24. Actually, it's more than a question that is gonna be related to it from chapter 24. Chapter 24, chapter 38, sorry. Problem 24 from chapter 38. Okay.
Is this
So
for the
problem
discussion as well?
Yeah, discussion basically is now finish all of the math problems and basically make sure that you have an understanding of the problems. Don't just finish them just blindly, okay? You have to have an understanding of what we're doing. Okay, chapter 38. You have problem 24. You have 31. 31 is nice. Is a nice problem. Okay. And you guys start to think what my mind is. It's always geared towards stuff that has to do with astronomy. That's exactly what 31 does. And then problem 39. That's it. This chapter has like up to 45 problems, so it really doesn't have much of a. Okay, let me do 24 because of the fact that it has a. If the average frequency emitted by 120 white light bulb is 5 times 10 to the power 14, and 10% of the input power is emitted as visible light, approximately how many visible light photons are? No, this is not exactly what I had in mind. Sorry about that. It's basically NC squared, okay? Oh, I'm sorry, this is for chapter 39. Okay, chapter 37. We're gonna come back to this idea, okay? Skip it for right now. Let's skip just to problem 31, and then I'll talk about the idea that is related to the post-test, okay? The idea that is related to the post-test, so that we start with it before I forget it, is the fact that the wavelength shift due to the Compton scattering is 2.42, 7 times 10 to the negative 12 meters times 1 minus cosine theta. If you remember from your pre-test, you were given a condition onto waves. They gave you lambda. I don't remember. Let's, for example, take it of the order of 10 to the negative 12 meters, okay? And they ask how much is going to be scattered in the theta equals to 90 degrees, basically perpendicular to the original direction. So here is the photon. The scattered electron is somewhere in here, but the photon is going to be now at 90 degrees. So the measurements, the observations are at 90 degrees exactly. Obviously, from this calculation, lambda prime will be just simply equal to this number, whatever number they gave you in here, plus this number, because when you move this, cosine of 90 degrees is 0. That's the whole point. So all you have to do is just add these two numbers to one another. So whatever number they gave you in here, let's say, for example, a wavelength of, I don't know, let's say, for example, 0.7, or no, not 0.7, that's too energetic. 7 times 10 to the negative. So it's going to be 7 plus 9 or 8 plus this number. So whatever that number is. You guys understand what this thing is trying to say to you guys, that you know this formula? And you know how to put cosine of theta equal to 90 degrees?
Right. So the issue, so I get the idea. It's just so when we substitute the cosine of 90 in there.
Let me go to the pretest so that we have the question.
Yeah, so what I'm trying to understand here, so when you substitute 90 degrees in for the cosine of 90, so then you get that's equal to 0. But then that number is just like pretty small in itself, right? So it can it be considered as insignificant? You can't really, it doesn't really make much of a difference, or does it really?
No, not for the not for the wavelength they gave you. Hold on. Let me get into the question itself, because sometimes this can be tricky. Not for the wavelength. The wavelength they gave us actually is a big wavelength. So let me share. Let me first of all find the pretest, and let me preview it. Yeah, begun. Come on, let's get going. Okay, and let me share now the pretest, because I want to share anything else. Share. Okay. So this question is easy in here. It says that how much heat energy. So this is the stuff we covered up to this point. How much heat energy must be removed from 100 grams of oxygen at 22 degrees to liquefy it at negative 183 degrees. So basically, in this case, you have the specific heat, you have the latent heat, and you have 100 grams of oxygen. So you have 100 grams times 0.218, which is 21.8, times the difference between 22 minus 183. So that's the delta T, plus 100 grams times the latent heat, which is 50.9. So that you add up the numbers and you should be able to compare them. So this is from specific heat, from calorimetry, yes?
Yes.
Okay, so this is easy. Yeah, I did not submit an answer because I didn't do the calculation. Next. Okay, so in here, it's asking you a heat engine exhausts 3000 joules of heat while performing 1500 joules of useful work. So this is the pretest. I'm not talking about the post-test. The post-test questions might be different, okay? So you have to be careful with that. So in here, a heat engine exhausts 3000 joules of heat while performing 1500 joules of, so in this case, what is the efficiency? The efficiency is the thing desired, which is the 1500 joules, divided by the heat absorbed. So this is the heat, this is QC, this is the exhaust. So it must have absorbed 3000 plus 1500, that gave me 4500. So the efficiency should be 1500 over 4500. Make sense? I think this should be correct in here, around 0.33, 33%. Sounds good?
Yes.
Okay, the next. Okay, here is the question that I skipped and I was thinking to do, and that's what I was thinking problem 24 does, but it doesn't. It tells you a nuclear bomb releases 1 megajoules of energy, how much mass that is. So basically you put 1 megajoules, which is 10 to the power 6 joules, equals to m times c squared. And c squared is 9 times 10 to the power 16. So you divide 10 to the power 6 divided by 10 to the 9 times 10 to the power 16, and you're going to find a number in here. Okay, choose one of them. It should be one of the 1.1s, not the 9. Okay, because you're inverting, dividing this by 9. Okay, it's either 10 to the negative 12, or 10 to the negative 11, or 10 to the negative 10. And I think this is the correct answer. No, actually, it's this one. Okay, sounds good.
Yeah, sounds good.
All right.
Yeah. So this is everything sounds easy that even I can do this. Okay. 4. Okay, here is a question. So they gave you an X-ray of 0.0650 nanometer. Undergo Compton scattering from the free electron in carbon. What is the wavelength of the 90-degree scattered photons? So they gave us lambda, and they want to know lambda prime, knowing that theta is 90 degrees. So that is, we add 0.065 nanometers to that 2.470, 2.4270 picometers. And we'll find a significant change in here, okay? So it's not this one. It's probably one of these two numbers in here, okay? Because it's going to be added. It's going to be longer. So you know up front it cannot be this one. It cannot be this one. It's either this or that because the wavelength has to be bigger. Okay. At most is going to be the same because of the fact that if theta is equal to 0, 1 minus 1 cosine of 0 is going to be 0, so it's going to be the same thing. So on the, looking straight ahead, we're going to find the same radiation, the same wavelength. But anything else is going to be more. And the only two more are these two guys. So these two cannot be. So let's go back, stop sharing. So we know lambda now, 0.065 nanometers. And they want the answer in nanometers. So lambda is 0.0650 nanometers, or 10 to the negative 9. Let me share the screen. So it's a nanometer plus 2.427, 10 to the negative 12, okay? Because theta is 0. I mean, cosine theta is 0, because theta is 90 degrees. So in this case, move the decimal points 3 times. So 1, 2, 3. So it's 65 nanometers plus 2.427 nanometers. I'm in picometers, I'm sorry. We're moving into picometers. Everything is in picometer now. 65 plus 2, that's 67.427 picometers. Move the decimal points 3 times. No, it's in here. There is a 2 in here, 4. Okay. So move the decimal point 3 times to get it back in nanometers because the choices were given to you in nanometers. So again, 1, 2, and 3. So the answer is in nanometer now. So 0.0672. So that's the choice that I have to pick in here. 0.67. Did I? No, 4, you're right. Because 2 plus 5 is 7, and 4 is in here, 4. Yes. So the correct answer is 0.0674 nanometer. That's the choice that you have. The closest choice to the correct answer. That's the one. You guys got it? Or should I go more in detail about it? So it's straightforward, really. So if theta was saying, for example, is equal to 0 degrees, then it's the same. Lambda and lambda prime are the same. If theta anything but that, then lambda prime must be longer. So you can eliminate anything, all the 3 of them, including the one that is equal. Because theta is not equal to 0. So you'll only have 2 choices to choose from, either the very long or the slightly longer. And that depends on theta, actually. If theta was equal to 180 degrees, well, 1 minus 1 is going to be twice this number. So you'll have to add 5, which is 2.4 times 2. That's about 5 plus 5. So it's going to put it around 69. So the correct answer should be 69, then 0.9 or 70, basically, 0.70, basically, nanometers. Okay, not this one. So it's actually the second choice. So this is really from that what I wanted to talk about really quickly. And I think the time is getting a little longer now. So hopefully you can get problem 31, and then the rest of them you can watch the other screens. And as a matter of fact, problem 31, we don't do it in detail. So 31. Nuclear fusion reactions at the center of the sun produce gamma rays. Here is a problem for 31. Inside the core of the sun, basically the proton-proton chain, which is the 4 protons getting together and forming the helium atom, basically, they're associated with other emissions in here that neutrino and other stuff. And actually, so this is basically what's happening inside the core of the sun. And that is the light that you see right now outside in your window. That is the light that came from there. Of course, the neutrinos also is another product in here that we're going to talk later on about. It actually is an anti-neutrino, not a neutrino. Okay. The problem with this reaction in here, it produces gamma rays. Gamma rays are not visible. You cannot see them. So how in the world we see stuff in here? How come we see the light that is actually in the visible range? That is the question from 31. So the way it's explained is that the radiation that comes from this process is very high energy, very short wavelength, but goes through Compton scattering, because inside the core of the sun, it's full of electrons and positrons. So it's going to scatter immediately when it hits an electron. And the wavelength is going to get longer. So lambda prime that is going to come out of it is longer than lambda. Of course, the electron is going to be bumped. But the point being in here is, and that's really the one that carries the excess energy from the gamma rays and short length and the wavelength, is this one. So lambda is shifted so that at some point it becomes in the visible range that we can see stuff with. This process takes a long time for it. According to this problem, it takes a million years. According to studies, it takes about 100,000 years for light to leave finally the sun and come to us. So the light that you see hitting your window or your screen or wherever you are right now from the sun was not produced now, was not produced 8 minutes ago, was not produced a year ago. It was produced 100 to 1 million years ago inside the core of the sun, and went through so many Compton scatterings to change its wavelength to become visible so that our eyes are sensitive to it. So that is basically in a nutshell what this problem is. So for this wavelength to go through Compton scattering, but we see it in the 500 nanometer range. Okay. That is basically the blue light, the regular light. This is in the visible region. Okay. The simple model that explains this difference in wavelengths is that a photon undergoes Compton scattering many times, in fact, about 10 to the power 26 times. So this is not only one, it's about 10 to the power 26 times, as suggested by the model of the source, as it travels from the center of the sun to its surface. Estimate the increase in wavelength of a photon in an average Compton scattering event. So basically, let's say, for example, it's in gamma rays. Gamma rays is the order, the lambda is of the order of 10 to the negative 12 meters, okay? And we want it to reach 500, so lambda prime, we want it to reach finally 500 times 10 to the negative 9 meters. So this is really how much we want to increase the wavelength from 10 to the negative 12 meters all the way up to 10 to the negative 9 meters, actually 10 to the negative 7 meters. Okay, so so the increase in wavelength, lambda difference basically between lambda prime and lambda is anywhere, the final wavelength will be 5 times 10 to the negative 12 meters. Obviously, this number is so tiny. It's going to be mainly the lambda prime, which is 500 nanometers, because this number is a very tiny one. So you have to increase it so much, really, that's all. You have to take it so much to take it from 10 to the negative 12 meters to 10 to the negative 7. Obviously, this takes 10 to the power 26. So in every this is not a single event. This is 10 to the power 26 single scattering. Is going to be this difference, which is lambda prime minus lambda divided. Increase in a single scattering would be this difference, which is roughly 500 nanometers. Again, sorry about that. Is it same? It's still doing it? Is it better now? Is it still or not?
Hello?
Is it still doing it?
Oh, yeah, now I can hear you.
Okay, sorry about that. So again, every scattering we'll see the big shift. This is the delta lambda, by the way, I should call it delta lambda at the end. This is the final value. We want to bring it by 500 nanometers times 10 to the power 26. So in other words, for a single scattering, lambda prime minus lambda must be equal to 500 times 10 to the negative 9 meters divided by 10 to the power 26. And that should be 500 times 10 to the negative 26 plus 9. That's 35. Or 5 times 10 to the negative 33 meters. So every scattering makes a very, very small change in the wavelength. Because we want to bring it from gamma rays range to down to a visible range in 10 to the power 26 times scatterings like this one. So in each one of them has this much increment in the wavelength, 5 times 10 to the negative 33 meters. So every scattering will have a tiny lambda, a tiny theta with it. So this is exaggerated theta in here. So tiny theta, 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 until you get all of this. And it takes about 1 million years to go through the process until light leaves the sun. So I suggest, so estimate the increase. So that's how much increase per incident, per scattered photon. Find the angle in degrees with the photon is scattered in the scattering. And they tell you use the approximation that cosine of phi is equal to 1 minus phi squared over 2. So using cosine of phi, or theta in my case, I think it's theta. 1 minus theta squared, this is a Taylor. Okay, for cosine of theta. Theta must be in radians, by the way, to do the Taylor in here. So we're going to come back to this expression, lambda prime minus lambda is equal to 2.427 times 10 to the negative 12 times 1 minus theta squared over 2. And this number is tiny. This is 5 times 10 to the negative 33 meters. And this is in meters, by the way. Meters cancels meters. Obviously, I'm going to cancel the 1 minus. And at the end, I will find an equation for theta squared is equal to 2 times 5, which is 10, times 10 to the negative 33, divided by 2.427 times 10 to the negative 12. Negative 12 and negative 33. Actually, it's negative 32 because of the fact that I have in here 33 and negative 12 is about 10 to the negative 20. And then 1/4, which is 1 over 2.4, roughly 4. So I'm just getting an estimate in here of 4 times 10 to the negative 20. So theta must be of the order of 2 times 10 to the power negative 10 radians. So it's extremely small angle. Even if you want to convert it to degrees, even if you want to express it in degrees, you're going to multiply this number by 180 and divide it by pi, which is 3.14. Even in this terms, it's still 2/3, roughly about 2/3 of 10 to the negative 8 or degrees, okay? So it's extremely, extremely small angle, okay? And then it is estimated that a photon takes about 1 million years to travel from the core of the sun to the surface. Find the average distance that the light can travel. Obviously, 1 million years, the total time is 1 million years, and a year is 365.25 days times 24 hours a day times 3,600 seconds a minute, okay? So this is the number of seconds that it takes for light to travel to make 10 to the power 26 scatterings, okay? And we want to find it, how much is going to travel between scattering and scattering. So this is for a total of 10 to the power 26 scatterings. And we'll find the time between scatterings, because that's what the question is. So the time between scatterings is this number, 10 to the power 6 times this whole number in here, divided by 10 to the power 26. And when we add up all of these numbers, we find the time for it. And then we multiply it by the speed of light and we find the distance it travels. So the distance, you're going to multiply this number by c, so ct, which is equal to 10 times to the power 6 times this big number in here, divided by 10 to the power 26 times the speed of light, which is 3 times 10 to the power 8. This is 365 times 24 times 3600. That's that big number that I didn't really write in here. So hopefully you guys will finish this and you will find the distance is extremely short. So the photon, as it's created from the nuclear fusion, is going to travel immediately, is going to be bouncing. And if you were to see that light, which you can't, but if somehow you can see it, it's going to basically immediately after it comes from a collision, it goes to a second one, it goes to a second one. So the distance traveled in here, the mean free path is so short. That is the extent with which we can detect actually the sizes in there. So it's really, it stays forever, for a long, long time inside the core of the sun before finally it emerges from the sun. It takes about 8 minutes to travel 150 million kilometers to us. Okay. Which is the distance between the Earth and the Sun. This distance is roughly equivalent to how far you could see if you were inside the Sun and could survive the extreme temperatures. As your answer shows, the interior of the Sun is very, very opaque. Okay, so this is really the nutshell from this problem. Okay. The other problems, problem 35 is a data problem, so you could use Excel to help you with that. Problem 39 is a little bit, you need to use relativity for that. And I might think there is a recording for it, please watch it. And if you have difficulty with these problems, please let me know. You're not supposed to submit these problems that we didn't do in class, so just to verify the problems we did in class, make sure the numbers are completed. But the others, you're supposed to do them on your own or either in homework or an exam or something like this. Are we in good shape?
Yes.
Okay. We still have chapter 40 before we are ready. Yes, the ones we did, okay, Natasha. Yeah, those are the ones. 31 is from chapter 38, by the way, and the other two are from chapter 39. Sounds good, Natasha?
Yes, it sounds good.
Okay, so the point being in here is that we're ready to move on to chapter 40. Chapter 40 will deal with Schrodinger's equation. First of all, we're going to derive the expression for the Schrodinger's equation, and we're going to solve it in the 1D case for the free electron and for the electron inside a well, and inside also a barrier, potential barrier, and we will see the tunneling, basically how the electron tunnel. Once we're done with that, we should be able to get ready for the exam, exam 2. Okay.
Wait, so what are the discussion questions?
Is basically to complete the numbers.
Complete the numbers?
Yep. Yes.
All right, what numbers?
The problems we did. 62, 64, 31, the ones that Natasha mentioned.
Oh, okay, just those.
Yeah, those are the ones we did. Did we do something else?
Okay.
Sue? Okay, so okay, I don't know Spanish, okay, that's all I know. So if you guys write in Spanish, I have no idea what you guys are saying. Sorry about that. I wish I know it, I really do. Okay, so I'm gonna stop recording. And I will see you guys.